2,300,000 blocks of stone. That is the number. 2,300,000 individual pieces of limestone and granite, each one quarried from the earth, shaped by human hands, transported across the desert, and lifted into position with a precision that modern engineers study with something that borders on disbelief. The average block weighs 2.5 tons. Some weigh 15. The granite beams above the king's chamber weigh as much as 80 tons each, and they were transported from quarries at Aswan, more than 800 kilometers to the south, up the Nile, across the floodplain, and then lifted to a height of more than 60 meters above the desert floor. The numbers are striking, and the numbers are only the beginning. The Great Pyramid of Giza, the tomb of the pharaoh Khufu, the last surviving wonder of the ancient world, stands on the Giza Plateau on the western edge of modern Cairo. It was built approximately 4,500 years ago, during the 4th dynasty of the Old Kingdom, in a period when the tallest structures in the rest of the world were mud brick walls and timber longhouses. It stood 146 meters tall when it was completed, taller than any structure that human beings would build for the next 3,800 years until the construction of Lincoln Cathedral in England in the 14th century of the Common Era. Its base covers an area of more than 53,000 square meters, 13 acres of precisely leveled bedrock, on which the 4 sides of the pyramid were laid out with an accuracy that still astonishes surveyors. The base is leveled to within 2.1 centimeters across its entire surface. The sides are aligned to the 4 cardinal points of the compass, with an error of less than 3/60ths of a single degree. The pyramid was built in approximately 20 years. 20 years for 2,300,000 blocks. That is roughly 340 blocks per day every day for 20 years. 14 blocks per hour. 1 block every 4 minutes. Quarried, moved, lifted, placed for 2 decades without interruption. These numbers have haunted engineers, architects, historians, and dreamers for centuries. They have inspired awe. They have inspired disbelief. They have inspired, unfortunately, a cottage industry of pseudo-scientific nonsense that attributes the pyramid to aliens, to lost civilizations, to mystical forces, to anything except the people who actually built it. The Egyptians of the Old Kingdom, working with copper tools, stone hammers, wooden sledges, and the most powerful construction technology in the ancient world, organized human labor on a massive scale. By the end of tonight, you're going to understand how they did it. Not with aliens, not with lost technology, not with mysteries that cannot be explained. With stone and copper and wood and water and rope and ramps and sweat and the organizational genius of a civilization that was, in many ways, more sophisticated than we have been willing to admit. Before we get started, if you find these mysteries as fascinating as we do, take a second to like the video or subscribe. It is a simple action, but it genuinely helps this channel reach more curious minds like yours. The numbers define the pyramid, but they do not explain it. The explanation requires something more than mathematics. It requires an understanding of the civilization that produced the numbers, the political system that mobilized the resources, the religious conviction that motivated the effort, and the engineering tradition that made the execution possible. The Great Pyramid is not merely a pile of stones arranged in a geometric shape. It is the physical expression of an entire civilization's capabilities, its administrative sophistication, its logistical competence, its material knowledge, and its capacity for sustained, coordinated, large-scale effort over a period of decades. The pyramid is, in the most literal sense, a civilization made visible, the accumulated knowledge and ambition of the Old Kingdom Egyptian state, frozen in stone for the rest of eternity. The question of how the pyramid was built is therefore not merely an engineering question. It is a question about the nature of civilization itself, about what human societies are capable of when they organize themselves around a shared goal, commit their resources to a common purpose, and sustain their effort across generations. The pyramid is the answer to that question, and the answer is more impressive, more instructive, and more humbling than any alien theory or mystical explanation could ever be. Because the real story of the pyramid is not a story about impossibility. It is a story about possibility, about what happens when human intelligence, human organization, and human labor are directed toward a single monumental, audacious goal. The pseudo-scientific theories that have clustered around the Great Pyramid, the alien construction theories, the lost civilization theories, the mystical energy theories, are not merely wrong. They are a form of erasure, an erasure of the real builders, the real workers, the real engineers and administrators who conceived, organized, and executed the most ambitious construction project in the ancient world. Every time someone claims that the pyramid was built by aliens, they are erasing the quarrymen of Giza. Every time someone invokes a lost civilization, they are erasing the masons who shaped the casing stones. Every time someone attributes the pyramid to mystical forces, they are erasing Mera and his crew of 200 workers who spent their days loading limestone onto boats and transporting it across the Nile. The real builders deserve better. Their achievement deserves to be understood on its own terms, as a human achievement accomplished by a specific civilization at a specific moment in history, using specific tools and specific methods that the archaeological evidence has been steadily revealing for more than a century. Now let's begin. The Great Pyramid was not the first pyramid. It was not even the first large pyramid. It was the culmination of a building tradition that had been developing for more than a century. A tradition of experimentation, failure, innovation, and gradual refinement that produced, by the time of Khufu's reign, a construction methodology that was capable of building the largest and most precise stone structure in the ancient world. The story begins with Djoser, a pharaoh of the Third Dynasty who reigned approximately a century before Khufu, and whose architect, Imhotep, designed the first monumental stone structure in human history. The step pyramid at Saqqara, Djoser's tomb, was a revolutionary structure, but it was not built as a single unified design. It was built in stages, beginning as a flat-topped rectangular structure called a mastaba, and then being expanded, stage by stage, into a six-step pyramid that rose to a height of roughly 62 meters. The construction was experimental. The builders were learning as they went, developing the techniques of stone quarrying, stone cutting, stone transport, and stone placement that would eventually make the Great Pyramid possible. Imhotep was not merely an architect. He was an inventor, the person who figured out, for the first time in human history, how to build a monumental structure entirely from cut stone. The achievement was so remarkable that later generations of Egyptians would worship Imhotep as a god. The century between Djoser and Khufu was a period of intensive experimentation in pyramid construction, a period that produced both successes and failures, and that generated the technical knowledge that the builders of the Great Pyramid would eventually draw upon. The most instructive of these experiments were the pyramids of Sneferu, Khufu's father, the founder of the Fourth Dynasty, and the most prolific pyramid builder in Egyptian history. Sneferu built at least 3 pyramids, more than any other pharaoh, and the sequence of his constructions reveals a process of trial, error, and refinement that is the engineering equivalent of a research and development program. Sneferu's first pyramid, the Maiden Pyramid, located about 100 kilometers south of Giza, was originally designed as a step pyramid and was later converted to a true pyramid by filling in the steps with a smooth outer casing. The conversion was not entirely successful. The outer casing eventually collapsed, leaving the distinctive tower-like structure that stands at Maiden today. The collapse may have occurred during construction or shortly afterward, and it would have taught the builders a critical lesson about the importance of foundation, preparation, and the angle of inclination in determining the stability of a true pyramid. Sneferu's second pyramid, the Bent Pyramid at Dahshur, provides even more dramatic evidence of the learning process. The pyramid was begun at a steep angle of approximately 54 degrees, an angle that would have produced a taller and more imposing structure than the Great Pyramid itself. But partway through the construction, at a height of roughly 49 meters, the builders discovered that the foundation was not stable enough to support a pyramid at that angle. The structure was showing signs of stress. Cracks were appearing in the internal chambers, The walls were beginning to shift, and the builders faced a choice between continuing with a design that might collapse and modifying the design to ensure the structure's survival. They chose modification. The upper portion of the pyramid was built at a shallower angle of approximately 43 degrees, producing the distinctive bent profile that gives the pyramid its modern name. The bent pyramid is a monument to the builder's willingness to adapt, to recognize a problem, to accept that their original design was flawed, and to modify their approach in response to the evidence that the construction itself was providing. Sneferu's third pyramid, the Red Pyramid at Dashur, was the first true pyramid to be completed successfully. It was built at the shallower angle of approximately 43 degrees, the same angle as the upper portion of the bent pyramid, and it was completed without the structural problems that had plagued the earlier attempts. The Red Pyramid is, in a sense, the dress rehearsal for the Great Pyramid, the first demonstration that the Egyptians could build a true pyramid of monumental scale without catastrophic structural failure. The techniques that were perfected during the construction of the Red Pyramid, the methods of quarrying, transport, placement, and alignment that would be used at Giza, were the techniques that Khufu's builders inherited and refined. This sequence of construction, from Djoser's experimental step pyramid through Sneferu's three increasingly successful attempts to Khufu's masterpiece, demolishes the myth that the Great Pyramid appeared out of nowhere, that it represents an impossible leap in technology, or that it could not have been built by the civilization that claimed to have built it. The Great Pyramid was not a miracle. It was the product of a century of sustained engineering research, a research program that was funded by the wealth of the Egyptian state, staffed by the most skilled craftsmen and laborers in the ancient world, and driven by the religious conviction that the pharaoh's tomb was the most important structure in the kingdom. The political context in which the Great Pyramid was built is essential for understanding how such a massive project could have been conceived, funded, and executed. The Fourth Dynasty, the dynasty of Sneferu, Khufu, Khafre, and Menkaure, represented the peak of royal power in ancient Egypt. The pharaoh was not merely a political ruler. He was a living god, the incarnation of Horus on earth, the mediator between the human world and the divine order, the figure on whom the entire cosmological and political structure of the Egyptian state depended. The pharaoh's death was not merely a political succession. It was a cosmic event, a disruption in the relationship between the human and the divine that needed to be managed with the utmost care to ensure the continuation of the cosmic order. The pyramid was the instrument of this management, a structure designed to facilitate the pharaoh's transition from the earthly realm to the divine realm, to ensure his eternal survival among the gods, and to maintain the connection between the living and the dead that was essential to the functioning of the Egyptian religious system. The economic resources available to the Fourth Dynasty pharaohs were enormous. Egypt was the wealthiest and most productive state in the ancient Near East. Its agricultural surplus, generated by the annual flooding of the Nile, was sufficient to support not only the population, but also a large class of craftsmen, administrators, priests, and laborers who were not engaged in food production and who were available for state projects. The pharaoh controlled these resources directly through a system of taxation, labor conscription, and state management of agricultural production that gave the central government access to the surplus labor and surplus wealth of the entire country. The construction of the Great Pyramid was therefore not an impossible burden on the Egyptian economy. It was a large but manageable expenditure of resources that was funded by the considerable surplus production of one of the most fertile and productive agricultural regions in the ancient world. The administrative apparatus that managed the construction was a bureaucracy of extraordinary sophistication. The Egyptian state of the Old Kingdom was among the very first large-scale bureaucracies in human history, a highly centralized administrative system that employed many thousands of scribes, accountants, managers, and officials who tracked the movement of goods, the allocation of labor, and the progress of state projects with a precision that is documented in the administrative papyri that have survived from the period. The Diary of Mera, the papyrus discovered at Wadi al-Jarf, is a product of this bureaucracy, and its detailed, matter-of-fact account of the daily operations of a limestone transport crew provides a glimpse of the administrative infrastructure that made the pyramid's construction possible. The bureaucracy was the invisible technology behind the visible technology of ramps and sledges, the organizational framework that carefully coordinated the efforts of tens of thousands of workers and ensured that the right materials arrived at the right place, at the right time, in the right quantities. The religious motivation that drove the construction cannot be separated from the practical logistics that made it possible. The Egyptians did not build the Great Pyramid because they had nothing better to do with their surplus labor. They built it because they believed, with a conviction that is difficult for modern secular observers to fully appreciate, that the pharaoh's tomb was the most important structure in the kingdom, that the proper burial of the king was essential to the maintenance of cosmic order, and that the resources devoted to the construction were an investment in the eternal well-being of the nation as a whole. The pyramid was not a vanity project. It was a national priority, a project that commanded the resources and the attention of the entire state, because the state believed that its survival depended on the successful completion of the pharaoh's eternal resting place. The choice of the Giza Plateau as the site for the Great Pyramid was the result of careful geological and logistical analysis. The plateau's limestone bedrock was not merely a convenient source of building material. It was also a structurally stable foundation that could support the enormous weight of the pyramid without settling or shifting. The bedrock was tested before construction began. Core samples were taken, the quality and the consistency of the stone were assessed, and the surface was carefully leveled to ensure that the pyramid's base would be flat and stable. The preparation of the site was itself a major engineering project. The plateau was cleared of loose debris, the surface was leveled using the water channel technique, and the bedrock was shaped to accept the first course of blocks with a precision that ensured the structural integrity of the entire structure. The timeline of pyramid development from Djoser to Khufu reveals something that is often overlooked in popular accounts of the Great Pyramid: the sheer quantity of institutional learning that preceded its construction. The Egyptians did not wake up one morning and decide to build the largest stone structure in the world. They worked toward it, methodically, patiently, and with a willingness to learn from failure that is one of the most admirable features of the Old Kingdom building tradition. The Maidam collapse taught them about foundation preparation and casing stability. The bent pyramid taught them about load distribution and angle management. The Red Pyramid taught them how to complete a true pyramid of monumental scale without structural failure. Each project added to the institutional knowledge base. Each success confirmed a technique. Each failure identified a limitation, and the cumulative result was a body of practical engineering knowledge that was, by the time of Khufu's reign, sufficient to support the construction of the most ambitious building project in human history. The critically important role of the vizier, the chief administrator of the Egyptian state, in managing the construction of the Great Pyramid was almost certainly central, though the specific individual who held the position during the construction is not known with certainty. The vizier was the pharaoh's chief executive officer, the official who managed the day-to-day operations of the state, who supervised the provincial governors and the department heads, who adjudicated disputes, and who oversaw the execution of the pharaoh's commands. The construction of the Great Pyramid would have been among the vizier's most important responsibilities, a project that required the coordination of every major department of the state, from the treasury to the granaries to the military to the provincial administration. The vizier was, in effect, the project manager, the person who translated the pharaoh's vision into an operational plan, and who ensured that the plan was executed on schedule and within the resources available. The rope supply was another essential element, often overlooked in popular accounts. Ropes were needed in enormous quantities for hauling sledges, lifting blocks, lashing scaffolding, securing loads on boats, and countless other purposes. The ropes were made from papyrus, hafa grass, and palm fiber, locally available, but requiring extensive processing before they could be twisted into ropes strong enough for construction loads. The rope-making operation employed hundreds of workers who harvested raw materials, processed fibers, and twisted them into ropes of various thicknesses for the diverse demands of the project. The consumption of rope was continuous and prodigious. A single day's operations could wear through hundreds of meters of rope, requiring constant production to maintain the supply. The surveying and alignment of the pyramid's base was one of the most technically demanding aspects of the entire construction process, and one of the most impressive in terms of the accuracy that was achieved. The base of the pyramid is a nearly perfect square, its four sides measuring approximately 230 meters each, with a maximum variation between the longest and the shortest side of less than 5 centimeters. The alignment to the cardinal points is accurate to within 3/60ths of a degree, an accuracy that was almost certainly achieved through astronomical observation rather than magnetic compass, since the magnetic compass was not invented for another 3,000 years. The method by which the alignment was achieved has been the subject of scholarly debate, but the most widely accepted hypothesis involves the observation of circumpolar stars. The builders would have observed a star near the north celestial pole, possibly Thuban, which was the pole star during the Old Kingdom, and used its position to establish a true north-south line. The east-west line would then have been established at right angles to the north-south line using the simple geometric principle that a perpendicular to a straight line can be constructed using nothing more than a rope and 2 stakes. The method was simple. The execution was extraordinary. The accuracy of the alignment demonstrates a level of care and precision that went far beyond what was structurally necessary, and that reflects the builder's commitment to perfection as both an engineering standard and a religious obligation. The logistics of tool maintenance during the construction process illustrate the scale and the complexity of the support infrastructure that the pyramid required. Copper was the hardest metal available to the Old Kingdom Egyptians. Iron smelting would not be developed in Egypt for another millennium, and copper chisels were the primary cutting tools used in the quarrying and shaping of limestone blocks. But copper is soft, far softer than the stone it was used to cut, and the chisels dulled rapidly during use, requiring constant resharpening. The resharpening was done by metalworkers who maintained forges at the construction site. Forges where the dulled chisels were heated, hammered back into shape, and returned to the quarrymen for further use. The cycle of dulling and resharpening was so rapid that the metalworkers constituted a significant proportion of the workforce, their labour as essential to the construction as the labour of the quarrymen themselves. The consumption of copper was enormous. Thousands of chisels were needed simultaneously, and the rate of wear was such that each chisel had a useful life of only a few hours before it needed to be resharpened. The copper supply chain, from the mines of Sinai to the forges at Giza, was therefore a critical element of the construction infrastructure, and any disruption in the supply of copper would have brought the quarrying operation to a halt. The timber supply was another critical logistical challenge. Wood was scarce in Egypt. The native trees were small, and their wood was unsuitable for the heavy-duty applications that the construction required. The sledges that were used to transport the blocks, the levers that were used to position them, the scaffolding that may have been used during the finishing of the casing, and the rollers that may have been used to facilitate the movement of the sledges, all required timber of a size and a quality that was not available from Egyptian sources. The timber was imported, primarily from Lebanon, where the famous cedars provided wood of the size, the strength, and the straightness that the construction demanded. The import of Lebanese cedar was a major diplomatic and commercial undertaking. It required negotiations with the rulers of the Levantine city-states, through which the timber was transported, the organization of shipping to carry the logs across the Mediterranean and up the Nile, and the maintenance of the trade relationships that ensured a reliable supply throughout the 20-year construction period. The harbour system that connected the construction site to the Nile was another critical element of the infrastructure. Recent archaeological work including excavations by Mark Lehner and Pierre Tallet, has revealed the remains of a harbour complex on the eastern edge of the Giza Plateau, connected to the Nile by a system of canals that allowed boats carrying limestone, granite, and other materials to deliver their loads directly to the base of the construction site. The harbour was operational during the annual flood season. When the Nile rose and the canals filled with water, the boats could navigate from the river to the harbour without the need for overland transport. The system was elegant and efficient. It used the natural flooding of the Nile to create a temporary waterway that connected the quarries and the supply depots to the construction site, dramatically reducing the effort required to move heavy materials from their sources to the pyramid. The Giza Plateau, the site that Khufu chose for his pyramid, was itself a carefully considered choice. The plateau offered several advantages that made it ideal for monumental construction. The bedrock was limestone, the same material that would constitute the vast majority of the pyramid's blocks, which meant that much of the stone could be quarried on site, rather than transported from distant locations. The plateau was located on the west bank of the Nile, a side associated with death and the afterlife in Egyptian religious thought, and it was close to the capital at Memphis, which ensured that the administrative apparatus of the state was within easy reach of the construction site. The plateau was elevated above the Nile floodplain, which meant that the annual flood, which inundated the lowlands for several months each year, would not reach the construction site, but would bring the river closer to the plateau, facilitating the transport of materials by boat. The organizational challenge of building the Great Pyramid was, in many ways, more formidable than the engineering challenge. The construction required not merely the physical placement of 2,300,000 blocks of stone, but the coordination of a labor force of tens of thousands of people, workers who needed to be recruited, transported to the site, housed, fed, organized into teams, supervised, and supplied with the tools and materials they needed to do their work. The construction required a supply chain that stretched the entire length of Egypt, from the granite quarries at Aswan in the south to the limestone quarries at Tura on the east bank of the Nile, from the copper mines of Sinai to the forests of Lebanon, where the timber for sledges and rollers was sourced. The construction required an administrative apparatus, scribes, accountants, foremen, and managers that could track the progress of the work, allocate resources efficiently, and solve the inevitable problems that arose during a project of this scale and duration. The system of labor conscription that supplied the workforce for the Great Pyramid was known as the corvée, a system in which the state required its subjects to contribute a period of labor to public works projects in lieu of, or in addition to, other forms of taxation. The corvée was not unique to Egypt. Similar systems existed in Mesopotamia, in the Inca Empire, and in medieval Europe. But the Egyptian version was particularly well organized and particularly effective, capable of mobilizing tens of thousands of workers for sustained periods and deploying them on projects that required a high degree of coordination and specialization. The corvée operated on a rotational basis. Workers were recruited from their villages and transported to the construction site for a period of several months, probably during the flood season, when the agricultural fields were underwater and the rural population was available for non-agricultural labor. After their period of service, the workers returned home and were replaced by a new rotation of laborers from different villages. The rotation system had several advantages. It distributed the labor burden across the entire population rather than concentrating it on a single group. It ensured a constant supply of fresh workers, and it allowed the skilled core workforce to train the rotating laborers in the specific tasks that the construction required. The food supply for the workforce was itself a massive logistical operation. The bakeries at the workers' village at Giza were industrial-scale facilities, capable of producing thousands of loaves of bread per day, using standardized molds and assembly line techniques that maximized output and minimized waste. The breweries produced a nutritious, low-alcohol beer that served both as a beverage and as a source of calories. The brewing process converted grain into a liquid that was easier to transport and distribute than solid food, and that provided essential nutrients in a form that was palatable and satisfying. The meat supply came from cattle, sheep, and goat herds that were maintained near the construction site. The animal bones found in the workers' village indicate that the workers received regular rations of meat, a luxury that was not available to the general population. And that suggests the state placed a high value on maintaining the health and the productivity of its labour force. The medical care provided to the workers is another indicator of the state's investment in its workforce. The skeletal remains from the workers' cemetery show evidence of healed fractures, bones that were broken during the construction process, and that were set and immobilized while they healed, a procedure that required trained medical practitioners. And that demonstrates a commitment to the welfare of the workers that goes beyond what would be expected if the workforce were composed of expendable slaves. Some of the healed fractures show evidence of surgical amputation, limbs that were removed cleanly and that healed successfully, indicating that the medical practitioners at the site were capable of performing complex surgical procedures, and that the workers who required such procedures were given the time and the care they needed to recover. The discovery of graffiti in the stress-relieving chambers above the king's chamber provides another category of evidence for the organization and the identity of the workforce. The graffiti, written in red ochre on the surfaces of the granite beams, includes team names, dates, and directional marks that were used during the construction process to identify which blocks belonged to which teams and where they should be placed. The team names are particularly revealing. Names like Friends of Khufu and the Drunkards of Menkaure suggest a workforce that was organized into competitive teams, each with its own distinctive identity and its own strong esprit de corps. The names are human. They suggest workers who took pride in their teams, who competed with other teams for recognition, and who identified themselves not as anonymous labourers, but as members of named groups with specific roles in the construction process. The discovery of the workers' village at Giza, excavated by the American archaeologist Mark Lehner and the Egyptian archaeologist Zahi Hawass, beginning in the 1990s, transformed our understanding of the labour force that built the pyramids. The village, located south of the pyramid complex, contained the remains of barracks, bakeries, breweries, workshops, and storage facilities that housed and fed the workers during the construction period. The evidence from the village demolished one of the most persistent myths about the pyramids, the myth that they were built by slaves. The workers at Giza were not slaves. They were paid labourers, organised into teams with names like Friends of Khufu and Drunkards of Menkaure, workers who received rations of bread, beer, and meat that were generous by the standards of the ancient world, and who were buried in a cemetery near the site when they died, with simple but respectful funerary provisions that indicate they were valued members of the community rather than disposable forced labourers. The evidence from the workers' village also provides insight into the scale of the labour force. Lehner has estimated that the permanent workforce at Giza numbered approximately 4,000 skilled workers, masons, quarrymen, surveyors, and other specialists who lived at the site year-round and who constituted the core of the construction team. This permanent workforce was supplemented by a rotating force of temporary workers, farmers and labourers, who were recruited from across Egypt during the annual flood season when the agricultural fields were underwater and the rural population was available for state labour projects. The total workforce at any given time may have numbered 20,000 to 30,000 people, a large number, but far smaller than the hundreds of thousands that Herodotus claimed and that popular imagination has assumed. The core problem of the Great Pyramid is not whether the Egyptians built it. They did. The evidence is overwhelming, archaeological, inscriptional, material, and contextual. The core problem is how. How did a civilization working with copper tools and human muscle move and place 2,300,000 blocks of stone in 20 years? How did they achieve a level of precision in the alignment of the base, the angle of the sides, and the placement of the internal chambers that would challenge a modern construction firm working with laser levels and GPS. How did they lift 80-ton granite beams to a height of 60 meters without cranes, without pulleys in the modern sense, and without any of the mechanical advantages that we take for granted in contemporary construction? The problem is not that we have no answers. The problem is that we have too many. Dozens of theories have been proposed over the past 2 centuries, each one claiming to solve the mystery of the pyramid's construction, each one marshalling evidence in its favor, and each one failing, in one way or another, to provide a complete and fully convincing account of how the entire project was executed from beginning to end. But here's the problem. The debate about the pyramid's construction has been distorted by 2 opposing tendencies, both of which are wrong. The first tendency is mystification. The impulse to treat the pyramid as an unsolvable mystery, to claim that its construction is beyond explanation, and to invoke supernatural or extraterrestrial explanations for what was ultimately a human achievement. This tendency is wrong because it denies the intelligence, the creativity, and the organizational genius of the Egyptian civilization that built the pyramid. The second tendency is oversimplification and the impulse to claim that the pyramid was just a pile of rocks that anyone could have built with enough labor, to dismiss the engineering challenges as trivial, and to treat the construction as a brute force exercise that required nothing more than a large workforce and a long time. This tendency is equally wrong because it ignores the extraordinary precision of the construction, the sophisticated engineering solutions that the builders employed, and the organizational complexity of a project that required the coordination of tens of thousands of people over 2 decades. The truth lies between these extremes. The Great Pyramid was built by human beings using the technology available to them. The technology was limited: copper tools, stone hammers, wooden sledges, rope, and water. But the technology was supplemented by something that modern commentators consistently underestimate: knowledge. The builders of the Great Pyramid possessed an understanding of geometry, materials science, logistics, and project management that was, in many ways, more sophisticated than anything that existed elsewhere in the ancient world. They did not need modern technology because they had something that modern technology sometimes replaces: a deep, practical, hard-won understanding of how stone behaves, how forces distribute, how water level surfaces, and how human labor can be organized to achieve results that seem, from a distance of 4.5 millennia, almost impossible. The ramp problem. The question of how the blocks were raised from ground level to the upper courses of the pyramid is the central engineering question of the Great Pyramid's construction, and it is the question that has generated the most sustained and the most contentious debate among scholars, engineers, and architects. The mathematics of the ramp problem are straightforward but unforgiving. The pyramid rises at an angle of approximately 51 degrees and 50 minutes, an angle that is too steep for teams of workers to drag heavy blocks directly up the face of the structure. Some form of ramp, an inclined surface at a gentler angle, was almost certainly required to move the blocks from ground level to their final positions. But the design of the ramp is constrained by a set of competing requirements that are difficult to reconcile. The ramp must be long enough to achieve a manageable slope, wide enough to accommodate the movement of heavy blocks, strong enough to support the weight of the blocks and the workers, and yet compact enough not to require more material than the pyramid itself. The debate about the ramp design has produced a literature that is vast, detailed, and frequently contentious. Engineers and architects from around the world have proposed solutions, some based on historical analogies, some based on mathematical modeling, some based on experimental archaeology, and some based on pure speculation. The theories range from the plausible to the fantastical, and the debate shows no sign of reaching a definitive resolution, in part because the evidence that would settle the question has been largely destroyed by the construction process itself, as the ramps were presumably dismantled and their materials reused after the pyramid was completed. The lever theory, proposed by various scholars as an alternative or supplement to the ramp theories, suggests that the blocks were raised using a system of wooden levers that tilted and lifted each block from one course to the next. technique is described by the Greek historian Herodotus, who visited Egypt in the 5th century before the Common Era, and who wrote that the pyramid was built using machines formed of short wooden planks that lifted the blocks from level to level. The lever theory has the advantage of simplicity. It requires no massive ramp infrastructure and can be applied at any height, but it has the disadvantage of speed. Lifting blocks one at a time using levers is a slow process, and it is difficult to see how the method could achieve the rate of block placement, approximately 340 blocks per day, that the construction schedule required. The most likely explanation is that no single method was used throughout the construction. The lower courses of the pyramid, which contain the largest number of blocks but which are closest to ground level, were probably built using external ramps of one kind or another. The upper courses, which contain fewer blocks but which require greater lifting heights, may have been built using a different method, possibly an internal ramp of the kind proposed by Houdin, possibly a system of levers and counterweights, or possibly a combination of techniques that varied depending on the specific requirements of each stage of the construction. The flexibility of the construction methodology, the willingness of the builders to adapt their methods to the specific challenges of each phase of the project, is itself one of the most impressive aspects of the Great Pyramid's construction. The builders were not dogmatic. They did not commit to a single method and then stubbornly apply it, regardless of circumstances. They were pragmatic. They used whatever method worked best for the specific task at hand, adapting their approach as the pyramid grew and as the engineering challenges changed from one phase of the construction to the next. The precision of the pyramid's construction, the accuracy of its alignment, the consistency of its angle, the levelness of its base, raises questions that are distinct from the question of how the blocks were raised, and that require their own analysis. The precision was not accidental. It was the result of careful measurement, constant monitoring, and a commitment to accuracy that permeated every aspect of the construction process. The builders measured, they checked, they verified, they corrected. They maintained a standard of precision that was driven not by vanity but by structural necessity. Because a pyramid that is not aligned, that is not level, that does not maintain a consistent angle from base to apex, will not stand. The precision was not a luxury. It was a requirement, a structural necessity that the builders understood and that they enforced with the rigor of engineers who knew that the consequences of imprecision would be catastrophic. The quarrying process provides the first demonstration of this practical knowledge. The limestone blocks that constitute the vast majority of the pyramid's mass were quarried from the Giza plateau itself, from quarries located a few hundred meters south and west of the construction site. The quarrying method was straightforward but labor-intensive. Workers used copper chisels and stone hammers to cut channels into the limestone bedrock, channels that defined the size and shape of the block to be removed. Wooden wedges were driven into the channels and then soaked with water, the expansion of the wet wood creating enough force to fracture the stone along the cut lines. The block was then levered out of the quarry using wooden levers and ropes placed on a sledge and dragged to the construction site. The process was simple in concept but demanding in execution. The copper tools were soft, softer than the stone they were cutting, and they needed to be resharpened constantly, which required a large contingent of metalworkers who maintained the tools throughout the construction process. The cutting was slow. Each block required hours of patient chipping and hammering to free from the bedrock, and the sheer volume of stone that needed to be quarried, 2,300,000 blocks over 20 years, meant that the quarrying operation needed to be running constantly, with multiple teams working simultaneously at different locations in the quarry. The Herodotus account of the pyramid's construction, written in the 5th century before the Common Era, roughly 2,000 years after the pyramid was built, is the earliest surviving written description of the construction process and has been both a valuable source of information and a source of considerable confusion for modern scholars. Herodotus visited Egypt around 449 BC and recorded what he was told by Egyptian priests and guides about the pyramid and its builder. His account includes the famous claim that the pyramid was built by 100,000 men working in shifts of 3 months each, a number that modern scholars consider a significant overestimate, but that reflects the genuine impression that the pyramid made on ancient visitors. Herodotus also describes the use of machines to raise the blocks, short wooden planks that were used to lift the stones from one level to the next, a description that has been interpreted as a reference to some form of levering mechanism, though the exact nature of the device remains unclear. The value of Herodotus's account lies not in its technical accuracy, which is questionable at best, given that he was writing 2,000 years after the event and relying on information provided by people who had no direct knowledge of the construction process, but in the evidence it provides for the enduring impression that the pyramid made on visitors and for the kinds of explanation sense that were current in the ancient world for the pyramid's construction. The account demonstrates that the question of how the pyramid was built has been asked for at least 2,500 years, and that the answers have always been a mixture of genuine information, inherited tradition, and creative speculation. The ancient Egyptian understanding of the pyramid's construction was, by the time of Herodotus's visit, already fragmentary. The knowledge that had built the pyramid had been attenuated by 2,000 years of institutional change. The old kingdom state that had organized the construction had collapsed, been succeeded by the Middle Kingdom, which had itself collapsed, been succeeded by the New Kingdom, which had reached its peak and was declining. The priests and guides who spoke to Herodotus were drawing on a tradition that was ancient, even by their standards, a tradition that preserved some genuine information about the construction process, but that had also accumulated errors, embellishments, and misunderstandings over the centuries of transmission. The modern archaeological investigation of the Great Pyramid began in earnest in the early 19th century with the work of European explorers and scholars who approached the pyramid with the tools and the methods of the emerging discipline of scientific archaeology. The Italian explorer Giovanni Battista Belzoni entered the Pyramid of Khafra in 1818. The British colonel Richard William Howard Vyse used gunpowder to blast his way into the stress-relieving chambers above the King's Chamber in 1837, a destructive approach that would be unthinkable by modern archaeological standards, but that revealed the team name graffiti that confirmed the pyramid's attribution to Khufu. The British archaeologist Flinders Petrie conducted the first systematic survey of the Giza Plateau in the 1880s, measuring the pyramid with an accuracy that had never before been achieved and establishing the baseline data that all subsequent studies have relied upon. Petrie's survey was a landmark in the study of the Great Pyramid, not because it revealed any dramatic new features, but because it established, for the first time, the precise dimensions and the precise alignment of the structure with an accuracy that allowed meaningful engineering analysis. Petrie measured the base, the height, the angle of the sides, the dimensions of the internal chambers, and the orientation of the structure to the cardinal points, producing a set of measurements that demonstrated, quantitatively, the extraordinary precision of the pyramid's construction. Petrie's measurements showed that the builders had achieved levels of accuracy that seemed, to the engineers of the late 19th century, almost impossibly high. Levels that implied the use of sophisticated measurement techniques and a commitment to precision that went far beyond what the simple tools available to the builders should have been capable of producing. The transport of the quarried blocks from the quarry to the construction site required a different set of skills and a different set of technologies. The blocks were placed on wooden sledges, flat platforms that distributed the weight of the block across a larger surface area, and that could be dragged across the desert by teams of workers pulling on ropes. The key innovation was the use of water. Workers poured water on the sand in front of the sledge, which reduced the friction between the sledge and the sand by as much as 50%. This technique, which was depicted in an Egyptian tomb painting from the Middle Kingdom, showing workers pouring water in front of a sledge carrying a colossal statue, was simple, effective, and dramatically reduced the number of workers needed to move each block. The granite blocks that were used in the internal chambers of the pyramid, the king's chamber, the queen's chamber, and the grand gallery, presented a more formidable transport challenge because they came from the quarries at Aswan, more than 800 kilometers to the south. The granite blocks were quarried using a technique called pounding. Workers use balls of dolerite, a stone harder than granite, to pound out channels in the rock face, gradually separating the block from the surrounding stone through a process of controlled percussion. The technique was extraordinarily labor-intensive. A single granite block could take months to quarry, but the blocks were quarried during the flood season, when the Nile was at its highest and barges could carry the heavy stone downstream with the current, dramatically reducing the effort required for transport. The internal passage system of the Great Pyramid reveals another dimension of the builders' engineering sophistication. Their ability to create complex three-dimensional structures within the mass of the pyramid while maintaining the structural integrity of the surrounding stonework. The passages are not simple tunnels cut through solid rock. They are carefully constructed corridors, built course by course as the pyramid rose, with walls, ceilings, and floors made of precisely cut stone blocks that were integrated into the surrounding masonry, with joints so tight that they have maintained their integrity for 4.5 millennia. The descending passage, which leads from the original entrance on the north face down through the body of the pyramid and into the bedrock beneath it, was cut at a precise angle of approximately 26 degrees and 31 minutes. The angle is not arbitrary. It corresponds approximately to the angle at which the circumpolar stars would have been visible from inside the passage, a correspondence that may have had ritual significance related to the pharaoh's journey to the stars. The passage is narrow, approximately 1 meter wide and 1.2 meters high, and it descends for more than 100 meters before reaching the subterranean chamber, a rough-hewn room carved from the bedrock that may have been intended as the original burial chamber before the design was changed to include the upper chambers. The ascending passage, which branches off the descending passage and leads upward into the body of the pyramid, was originally sealed by 3 massive granite plugs that were slid down the passage after the pharaoh's burial to prevent access to the upper chambers. The plugs are still in place. They were bypassed by al-Mamun's tunnelers in the 9th century, who dug around them through the softer limestone rather than attempting to remove the granite blocks. The presence of the plugs demonstrates the builders' concern with security. Their awareness that the treasures buried with the pharaoh would attract robbers, and their determination to make the upper chambers as inaccessible as possible. The subterranean chamber, the lowest of the 3 known chambers, is one of the most enigmatic features of the pyramid's internal structure. The chamber is unfinished. Its walls and floor show the rough marks of the quarrymen's tools, without the smooth finishing that characterizes the king's chamber and the queen's chamber. The unfinished state of the chamber has been interpreted in various ways, as evidence that the original burial plan was abandoned in favor of the upper chambers, as evidence that the chamber was intentionally left rough for ritual purposes, or as evidence that the construction was interrupted before the chamber could be completed. The question remains unresolved, and the unfinished chamber stands as a reminder that even the most meticulously planned construction project can leave behind features that do not fit neatly into any single interpretive framework. The Queen's Chamber, located roughly 20 meters above ground level in the body of the pyramid, is another enigmatic feature. Despite its modern name, the chamber was almost certainly not intended for a queen. The name was assigned by Arab explorers who assumed that the smaller of the 2 upper chambers was the queen's burial chamber. The chamber's actual purpose is debated. It may have been an earlier burial chamber that was superseded by the king's chamber. It may have served a ritual function related to the pharaoh's funerary rites, or it may have housed a statue of the pharaoh that served as a focus for the rituals performed in the mortuary temple. The niche in the eastern wall of the chamber, a corbelled recess that may have held a statue, supports the statue hypothesis, but the evidence is not conclusive. The question of how the builders maintained the pyramid's angle, the consistent slope of approximately 51 degrees and 50 minutes, throughout construction is equally important for understanding the precision achieved. The angle had to be maintained across all four faces simultaneously. Any deviation would have been visible in the finished structure. The builders almost certainly used set squares, right-angled wooden triangles whose proportions defined the desired slope, checking the face angle at regular intervals and correcting any deviations immediately. The corners received particular attention as the geometric keystones where two faces met, and the surviving casing stones at the base confirm that corner blocks were cut with exceptional precision, tighter joints and smoother surfaces than the blocks along the faces. The copper tools that the quarrymen used, chisels, adzes and saw blades, were remarkable instruments despite their softness relative to the stone they cut. The effectiveness of copper tools on limestone depended not on the hardness of the metal alone, but on the technique of the quarryman, the angle of attack, the force of the blow, the rhythm of the cutting stroke. Experienced quarrymen developed an intuitive understanding of how limestone responded to percussion, where it would fracture cleanly, where it would crumble, where the grain of the stone ran in directions that facilitated cutting, and where it ran in directions that resisted it. This practical knowledge, the quarryman's feel for the stone, was as much a tool as the copper chisel itself, and it was knowledge that could only be acquired through years of hands-on experience. The distinction between a skilled quarryman and an unskilled one was not a matter of strength. It was a matter of knowledge, the accumulated, deeply embodied, intensely practical understanding of how stone behaves that allowed the skilled worker to produce a clean, square, accurately dimensioned block in a fraction of the time that an unskilled worker would require. The granite blocks posed an even greater challenge than the limestone. Their extreme hardness meant that copper tools were useless against them, and the pounding technique with dolerite balls was the only viable method for quarrying, a process that required extraordinary patience and physical endurance from the workers who performed it. The discovery of the Diary of Mera in 2013 transformed our understanding of the transport system that supplied the Great Pyramid with materials. The diary, a collection of papyrus fragments discovered at the ancient harbour of Wadi al-Jarf on the Red Sea coast, was written by an inspector named Mera, who supervised a crew of about 200 workers during the 27th year of Khufu's reign. The diary describes in detailed and mundane terms the daily operations of a team that was transporting limestone blocks from the quarries at Tura on the east bank of the Nile to the construction site at Giza. The diary records the loading of blocks onto boats, the journey across the Nile, the delivery of the blocks to the harbour near the construction site, and the return trip to the quarry to pick up another load. The diary is the most direct evidence we possess for the logistics of pyramid construction, a first-person account of the daily work of moving stone that confirms the basic picture that Egyptologists had reconstructed from archaeological evidence, and that adds a wealth of specific detail about the routes, the schedules, and the organization of the transport system. The engineering challenge of building the internal chambers of the Great Pyramid, particularly the King's Chamber and the Grand Gallery, was distinct from the challenge of building the external structure and required a different set of skills and a different approach to problem solving. The internal chambers had to be built as the pyramid rose. They could not be added after the structure was complete because the chambers are embedded within the mass of the pyramid and can only be accessed through the passages that were built simultaneously with the surrounding structure. This meant that the builders had to plan the internal layout of the pyramid in advance, designing the chambers, the passages, and the structural elements that would support them before the first block was laid, and then executing the plan with a precision that allowed no room for error, because any mistake in the placement of the internal elements would be buried beneath thousands of tons of stone and could not be corrected. The King's Chamber posed the most formidable engineering challenge. The chamber is built entirely of granite, red granite from Aswan, one of the hardest stones in Egypt, cut and polished to a smooth finish and fitted together with joints so tight that a piece of paper cannot be inserted between the blocks. The ceiling of the chamber consists of 9 granite beams, each spanning the full width of the chamber and each weighing between 25 and 80 tons. The beams had to be quarried at Aswan, transported 800 kilometers downstream on the Nile, hauled to the construction site, and then raised to a height of more than 40 meters above ground level, a feat that required not just brute force but careful planning, because the beams could not be dropped, tilted, or damaged during the lifting process without compromising the structural integrity of the chamber. Above the ceiling beams are 5 stress-relieving chambers, flat ceilinged spaces designed to distribute the weight of the pyramid above the king's chamber and to prevent the ceiling beams from cracking under the enormous compressive load. The uppermost of these chambers is topped by a gable roof, a peaked structure formed by leaning pairs of limestone blocks against each other at an angle, creating a void that deflects the downward force of the pyramid's mass to the sides of the chamber rather than directly onto the ceiling beams below. The stress-relieving system is one of the most sophisticated structural elements in the ancient world. It demonstrates an understanding of force distribution and load management that anticipates, by 4.5 millennia, the structural engineering principles that govern the design of modern buildings and bridges. The ventilation shafts, narrow channels that extend from the king's chamber and the queen's chamber through the body of the pyramid to the exterior surface, have been the subject of considerable scholarly debate. The shafts from the king's chamber were long thought to be ventilation channels designed to provide fresh air to the interior of the pyramid. But this interpretation has been challenged by the discovery that the shafts from the queen's chamber do not reach the exterior surface. They terminate within the body of the pyramid, sealed by stone plugs that prevent any airflow. The sealed shafts suggest that the channels served a ritual or symbolic function rather than a practical one, possibly serving as conduits for the pharaoh's soul to travel to the stars, a hypothesis that is consistent with the Egyptian religious belief that the pharaoh's eternal destiny was among the circumpolar stars of the northern sky. The question of how the builders maintained the pyramid's angle, the consistent slope of approximately 51 degrees and 50 minutes from base to apex throughout the construction process, is a question that has received less attention than the ramp question, but that is equally important for understanding the precision of the construction. The angle had to be maintained across all 4 faces of the pyramid simultaneously. Any deviation in one face would have been visible in the finished structure and would have compromised the geometric perfection that the builders sought to achieve. The maintenance of the angle required constant measurement, checking the slope of each face against a reference standard at regular intervals during the construction process. The reference standard was almost certainly a set square, a right-angled triangle made of wood or stone, whose proportions defined the desired slope angle. The builders would have placed the set square against the face of the pyramid at regular intervals, checking that the angle of the face matched the angle of the reference standard. Any deviation would have been corrected immediately by adding or removing material from the course under construction, by adjusting the placement of blocks to bring the face back into alignment. The process was labor-intensive and time-consuming, but it was essential because the cumulative effect of even small deviations would have been visible in the finished structure and would have compromised the pyramid's function as a demonstration of divine precision and cosmic order. The corners of the pyramid were the most critical points for maintaining the angle, because the corners were the intersections of 2 faces, and any error at a corner would have been amplified as the construction progressed upward. The builders appear to have paid particular attention to the corners. The remaining casing stones at the base of the pyramid show that the corner blocks were cut with exceptional precision, with joints that are tighter and surfaces that are smoother than those of the blocks along the faces. The care taken with the corners reflects the builder's understanding that the corners were the structural and geometric keystones of the entire structure, the points where accuracy was most critical and where errors would have the most visible and the most damaging consequences. And it gets worse, for the skeptics, that is, because the Diary of Mera does not describe a mystery. It does not describe an inexplicable process that required supernatural intervention. It describes a bureaucracy, a carefully organized, efficiently managed, thoroughly documented logistics operation that moved stone from quarry to construction site with the same methodical precision that a modern supply chain moves goods from factory to warehouse. The diary describes shift rotations, travel times, delivery schedules, and the names of the officials who supervised the operation. It is, in short, the papyrus equivalent of a shipping manifest, and its very mundanity is the strongest possible argument against the claim that the pyramid's construction was mysterious or inexplicable. But here's what makes this truly terrifying, in the best possible sense. The Diary of Mera was discovered by accident. The papyri were found in a sealed chamber at Wadi al-Jarf, a site that was not excavated until 2011, more than a century after the systematic archaeological exploration of Egypt began. The diary had been sitting in the ground for 4,500 years, waiting to be found. And when it was found, it answered questions that Egyptologists had been debating for generations, not with speculation or theory, but with the mundane, detailed, bureaucratic prose of a man who was doing his job and recording his work for his superiors. How much more evidence is still in the ground? How many more diaries, manifests, records, and accounts of the pyramid's construction are buried beneath the sand, waiting to be discovered? The Diary of Mera is a single document, a fragment of a vast bureaucratic apparatus that must have generated thousands of similar records over the 20 years of the pyramid's construction. Most of those records have been lost, destroyed by time, by humidity, by insects, by the simple fragility of papyrus over millennia. But some may survive, and every one that is recovered adds to our understanding of how the greatest building project in the ancient world was organized and executed. The question of how the blocks were raised, how 2,300,000 stones were lifted from ground level to their final positions, some of them at heights of more than 140 meters, is the question that has generated the most debate, the most theories, and the most disagreement among scholars, engineers, and architects who have studied the Great Pyramid. The first exploration examines the ramp theories, the family of hypotheses that propose that the Egyptians used inclined ramps of one kind or another to raise the blocks from ground level to the upper courses of the pyramid. The simplest ramp theory, the straight ramp, proposes that the Egyptians built a single long ramp that extended from the base of the pyramid to whatever level was currently under construction, and that the blocks were dragged up this ramp on sledges. The theory is intuitive and straightforward. A ramp is the simplest possible way to raise heavy objects to a height, and the Egyptians certainly knew how to build ramps, as evidenced by the construction ramps that have been found at numerous building sites across Egypt. But the straight ramp theory faces a fatal mathematical problem. To maintain a slope gentle enough for teams of workers to drag heavy blocks upward, a slope of no more than about 1 in 10, a ramp reaching the full height of the pyramid would need to be approximately 1.5 kilometers long. The ramp itself would require as much material as the pyramid, millions of cubic meters of earth, rubble, and brick that would need to be constructed, maintained, and then removed after the pyramid was completed. The logistics are implausible. The straight ramp, in its simplest form, does not work. The spiral ramp theory proposes that the ramp was built along the outside of the pyramid itself, wrapping around the structure in a spiral that allowed the blocks to be raised progressively as the pyramid grew. The spiral ramp solves the length problem. By wrapping around the pyramid, the ramp can achieve a gentle slope without extending far beyond the pyramid's footprint. But the spiral ramp creates a different problem. It would have covered the corners of the pyramid during construction, making it impossible for the builders to verify the alignment and the angle of the sides as the construction progressed. The precision of the Great Pyramid, the accuracy of its alignment to the cardinal points, the consistency of its angle from base to apex, suggests that the builders needed to maintain clear sight lines to the corners and edges of the structure throughout the construction process. A spiral ramp would have obstructed these sight lines. The internal ramp theory, proposed by the French architect Jean-Pierre Houdin in 2007, offers a potentially revolutionary solution to the ramp problem. Houdin proposes that the lower portion of the pyramid, roughly the bottom third, was built using a conventional external ramp, and that the upper two-thirds were built using an internal ramp, a spiral passage built into the body of the pyramid itself, through which the blocks were dragged to the upper levels. The internal ramp would have been invisible from the outside. It would have been built into the mass of the pyramid, with openings at the corners where the blocks could be turned and where the builders could verify the alignment of the structure. Houdin's theory is supported by several pieces of evidence, including microgravity surveys of the pyramid that have detected a spiral-shaped anomaly within the structure that is consistent with the presence of an internal passage and the existence of a notch at one of the corners of the pyramid, roughly one-third of the way up, that could be the remains of a turning station, where blocks were rotated from one section of the internal ramp to the next. The internal ramp theory has not been proven. It remains a hypothesis that would require physical exploration of the pyramid's interior to confirm or refute, but it represents the kind of creative, evidence-based thinking that has characterized the best scholarship on the pyramid's construction. The kind of thinking that treats the pyramid not as an unsolvable mystery, but as an engineering problem that can be analyzed, modeled, and ultimately understood. The second exploration concerns the precision of the pyramid's construction, the extraordinary accuracy that the builders achieved in leveling the base, aligning the sides, and maintaining a consistent angle from base to apex. The leveling of the base was almost certainly accomplished using water. The builders excavated a network of channels into the bedrock of the Giza plateau, channels that were filled with water, creating a perfectly level reference surface that could be used to ensure that the base of the pyramid was flat to within a few centimeters across its entire 53,000 square meter area. The technique was simple. Water always finds its own level, and a network of water-filled channels provides a reference surface that is as accurate as any laser level. The technique was also ancient. The Egyptians had been using water leveling for centuries before the construction of the Great Pyramid, and the refinement of the technique at Giza represents the culmination of a long tradition of practical hydraulic knowledge, the alignment of the sides to the cardinal points, the astonishing accuracy with which the pyramid's faces are oriented to true north, south, east, and west was probably accomplished using astronomical observations. The Egyptians were skilled observers of the night sky. They had been tracking the movements of the stars for centuries, and they had developed methods for determining true north by observing the positions of circumpolar stars as they rotated around the celestial pole. Recent research by the engineer Glenn Dash has proposed that the alignment may have been accomplished using the autumnal equinox, a method that involves marking the positions of the sun's shadow the moment of the equinox and using these marks to establish a precise east-west line from which the other cardinal directions can be derived. The method is elegant, accurate, and requires nothing more sophisticated than a vertical post, a flat surface, and careful observation. The third exploration examines the internal structure of the pyramid, the chambers, corridors, and passages that constitute some of the most remarkable architectural achievements within the structure. The internal structure of the Great Pyramid is unique among Egyptian pyramids and has been a source of fascination and speculation since the first explorers entered the structure in the 9th century of the Common Era. The pyramid contains 3 known chambers: the subterranean chamber, carved out of the bedrock beneath the pyramid, the Queen's Chamber, located in the body of the pyramid above the base, and the King's Chamber, located near the center of the pyramid at a height of roughly 43 meters above ground level. The chambers are connected by a system of passages. The descending passage, which leads from the entrance on the north, face down to the subterranean chamber. The ascending passage, which branches off the descending passage and leads upward to the Queen's Chamber and the Grand Gallery. And the Grand Gallery itself, a magnificent corbelled corridor that rises at a steep angle for 47 meters before terminating at the entrance to the King's Chamber. The Grand Gallery is one of the most impressive architectural spaces in the ancient world. It is 8.5 meters high, an enormous height for a corridor, and it is built using a corbelling technique in which each successive course of stones projects slightly beyond the one below it, gradually narrowing the space until it can be spanned by a single stone at the top. The corbelling is precise. Each course projects exactly 7 6/10 centimeters beyond the one below it, creating a smooth, symmetrical narrowing that is both structurally sound and aesthetically elegant. The Grand Gallery has been interpreted by some scholars as a functional element of the construction process, possibly a space used for the manipulation of counterweights that help to lift the massive granite beams above the king's chamber into position. The king's chamber itself is a masterpiece of granite engineering. The chamber measures roughly 10.5 meters by 5 2/10 meters, with a flat ceiling composed of 9 granite beams, each weighing between 25 and 80 tons. Above the ceiling are 5 stress-relieving chambers, spaces designed to distribute the enormous weight of the pyramid above the king's chamber across a wider area and to prevent the ceiling beams from cracking under the load. The stress-relieving chambers are one of the most sophisticated structural elements of the pyramid. They demonstrate an understanding of load distribution and structural engineering that was remarkably advanced for the period and that anticipated, by more than 4 millennia, the structural principles that modern engineers use in the design of buildings and bridges. The fourth exploration examines the workforce and the social organization of the construction project, the human dimension of the Great Pyramid's creation, the evidence from the workers' village at Giza, the barracks, the bakeries, the breweries, the workshops, paints a picture of a construction project that was organized with extraordinary efficiency and that treated its workers with a level of care and respect that belies the popular image of pyramid construction as a brutal exercise in forced labor. The bakeries at the workers' village were capable of producing thousands of loaves of bread per day, the staple food of the Egyptian laborer, supplemented by beer, meat, fish, and vegetables that were supplied by the state. The animal bones found at the site include cattle, sheep, goat, and fish, a varied diet that indicates that the workers were well fed by the standards of the ancient world. The workers were organized into teams, large groups of roughly 1,000 workers, each divided into smaller units of roughly 200, which were in turn divided into crews of roughly 20. Each team had a name, names like Friends of Khufu and the Drunkards of Menkar that suggest a spirit of camaraderie and group identity among the workers. The team names were inscribed on the blocks themselves, red ochre marks that have been found in the stress-relieving chambers above the king's chamber and in other parts of the pyramid, identifying the teams that place specific blocks and providing a direct connection between the anonymous mass of stone and the named organized human labor that put it there. The skeletal remains from the workers' cemetery near the village provide information about the physical condition of the laborers. The bones show evidence of healed fractures, arthritis, and the wear patterns associated with heavy physical labor, but they also show evidence of medical treatment, including the setting of broken bones and the treatment of injuries that would have been fatal without intervention. The workers were not disposable. They were valued. Their injuries were treated, their dead were buried with care, and their labor was organized in a way that suggests a concern for efficiency and sustainability, rather than the ruthless exploitation that the slave labor myth implies. The role of water in the construction of the Great Pyramid deserves particular attention because it illustrates the ingenuity with which the builders used simple natural phenomena to solve complex engineering problems. Water was used for multiple purposes throughout the construction process: for leveling the base, for reducing friction during transport, for quarrying stone, and possibly for raising blocks to the upper courses of the pyramid. The use of water for leveling has already been described. The builders excavated channels into the bedrock, filled them with water, and used the water surface as a reference to ensure that the base was flat. But water was also used in less obvious ways. The quarrying of limestone blocks involved the use of water-soaked wooden wedges. Wedges driven into channels cut in the rock face and then saturated with water causing them to expand and crack the stone along the desired fracture line. The technique required patience. The wedges needed time to absorb the water and to swell, but it was effective and reliable, producing clean fractures along predictable lines that allowed the quarrymen to control the size and shape of the blocks they produced. The transport of blocks on sledges was dramatically improved by the use of water poured on the sand in front of the sledge. Experiments conducted by physicists at the University of Amsterdam in 2014 confirmed what the Egyptian tomb paintings had depicted for centuries: that wetting the sand reduced the friction coefficient by approximately 50%, halving the number of workers needed to move each block. The experiment was simple. The physicist dragged a weighted sledge across a tray of sand, measuring the force required with and without water. The results confirmed that the addition of water transformed the dry, shifting sand into a firm, cohesive surface that allowed the sledge to glide smoothly, a technique that the Egyptians had clearly understood and exploited thousands of years before the physics of granular friction were formally described. The question of whether water was used to raise blocks to the upper courses of the pyramid has been explored by several researchers, with varying degrees of plausibility. Some have proposed that the blocks were floated upward using a system of water-filled locks or chambers, essentially an ancient version of a canal lock system. The theory is ingenious, but faces significant practical challenges. The volume of water required would have been enormous. The waterproofing of the chambers would have been difficult with the materials available, and the logistics of filling and draining the chambers would have added complexity to an already complex construction process. Most scholars consider the waterlifting theories implausible, but the fact that they have been seriously proposed and seriously analysed reflects the continuing vitality of the debate about the pyramid's construction methods. The granite quarrying at Aswan deserves its own detailed examination because it represents one of the most challenging aspects of the entire construction project. The granite blocks used in the King's Chamber, the Grand Gallery, and the stress-relieving chambers were quarried from the red granite deposits at Aswan, deposits that are among the hardest stones in Egypt and that required specialized techniques to work. The quarrying technique, pounding with dolerite balls, was brutally labor-intensive. Workers sat in rows along the quarry face, rhythmically pounding the granite with balls of dolerite, a stone that is harder than granite and that could therefore be used to chip and abrade the granite surface. The work was slow. A single block could take months to quarry, and it was physically demanding, producing the kind of repetitive strain injuries that have been documented in the skeletal remains from the workers' cemeteries. The transport of the granite blocks from Aswan to Giza, a distance of more than 800 kilometers, was accomplished primarily by water. The blocks were loaded onto barges at Aswan and floated downstream on the Nile, a journey that took advantage of the river's northward current to move the heavy loads with minimal human effort. The journey was long, several weeks at minimum, and it required careful navigation, particularly through the cataracts of the Nile, where the river narrows and the current becomes turbulent. The barges were large enough to carry blocks weighing up to 80 tons, and they were constructed of wood, using the techniques of Egyptian boat building that were among the most advanced in the ancient world. The discovery of the Khufu ship, a full-sized ceremonial boat that was found disassembled in a sealed pit at the base of the Great Pyramid in 1954, provides direct evidence for the scale and the sophistication of Egyptian boat building during the 4th dynasty. The ship is 43 meters long, large enough to be seaworthy, and certainly large enough to carry heavy cargo on the relatively calm waters of the Nile. The ship was built using a mortise and tenon technique. The planks were joined together without nails, using wooden pegs and rope lashings that allowed the hull to flex with the movement of the water. The ship demonstrates that the Egyptians of the 4th dynasty possessed the boat-building skills necessary to construct the barges that transported the granite blocks from Aswan, and it provides a physical, tangible link between the pyramid and the transport infrastructure that made its construction possible. The 5th exploration concerns the outer casing of the pyramid. the gleaming white limestone surface that originally covered the entire structure, and that has been almost entirely removed over the centuries. The Great Pyramid was not originally the stepped, rough surface structure that we see today. It was originally covered in a casing of fine white limestone, quarried from the Tura quarries on the east bank of the Nile and transported across the river to the construction site. The casing stones were cut and polished to a smooth, reflective finish, creating a surface that would have gleamed in the Egyptian sun, reflecting the light across the Giza plateau and visible from many kilometers in every direction. The pyramid was, in its original state, a monument of light, a structure designed to catch the rays of the sun and to transform them into a visible demonstration of the pharaoh's divine power and his connection to the sun god Re. The casing stones have been almost entirely removed, stripped from the pyramid over the centuries by successive generations of builders who used the high-quality limestone for their own construction projects. The most significant removal occurred during the medieval period, when the rulers of Cairo used the casing stones to build mosques, palaces, and the city walls. A few casing stones remain in place at the base of the pyramid, their smooth, angled surfaces providing a glimpse of the pyramid's original appearance and demonstrating the precision with which the casing was fitted. The joints between the casing stones are so tight that a knife blade cannot be inserted between them, a level of precision that implies the use of specialized finishing techniques and the work of master craftsmen whose skills were the product of generations of accumulated knowledge. The ancient boat pits discovered around the Great Pyramid provide evidence for the funerary beliefs and the construction capabilities of the Old Kingdom that complement the evidence provided by the pyramid itself. 5 boat pits have been identified around the base of the Great Pyramid, 2 on the south side, 2 on the east side, and 1 on the north side. The 2 southern pits contained full-sized boats, one of which was excavated in 1954 and reconstructed over a period of 14 years, emerging as the magnificent cedar vessel known as the Khufu ship. The second, the southern boat, was examined using a miniature camera inserted through a drilled hole in the pit's limestone ceiling in the 1980s and was subsequently excavated and is now undergoing conservation. The Khufu ship is one of the most remarkable artifacts of the ancient world, a vessel of extraordinary craftsmanship that demonstrates the sophistication of Egyptian boat-building technology during the 4th dynasty. The ship is 43.4 meters long and 5.9 meters wide, large enough to be functional on the Nile and possibly on the open sea. The hull is constructed of Lebanese cedar planks, joined together with mortise and tenon joints and laced with rope, creating a flexible structure that could absorb the stresses of water movement without rigid fasteners. The ship was found disassembled, its 1,224 individual components carefully arranged in the pit in a specific order that facilitated reassembly, strongly suggesting that the ceremonial boat was specifically intended to be used by the pharaoh in the afterlife, and that it had been dismantled for storage rather than for disposal. The boat pits demonstrate several genuinely important and revealing points about the Old Kingdom Egyptian civilization. They demonstrate the sophistication of Egyptian boat building, the ability to construct large, seaworthy vessels using techniques of joinery and lashing that were among the most advanced in the ancient world. They demonstrate the logistical capability of the Egyptian state, the remarkable ability to import very large quantities of high-quality timber from distant Lebanon and to employ skilled boat builders who could transform the timber into vessels of exceptional quality. And they demonstrate the depth of the religious beliefs that motivated the pyramid's construction. The belief that the pharaoh would need boats in the afterlife to travel through the celestial waters and the commitment of resources to providing those boats was as serious and as carefully executed as the commitment of resources to building the pyramid itself. The mortuary temple that was attached to the eastern face of the Great Pyramid has been almost completely destroyed, its blocks removed for reuse in later construction projects, leaving only the basalt floor of the temple and fragments of the walls that once enclosed it. The temple was the ritual center of the pyramid complex, the place where the daily offerings to the deceased pharaoh were prepared and presented, where the priests performed the rituals that sustained the pharaoh's soul in the afterlife, and where the living maintained their connection to the dead through the formalized ceremonial practices that the Egyptian religious system required. The destruction of the mortuary temple is one of the most significant losses associated with the Great Pyramid, because the temple contained the inscriptions, the reliefs, and the ritual objects that would have provided detailed information about the religious practices associated with the pyramid and about the beliefs that motivated its construction. The causeway that connected the mortuary temple to the valley temple near the Nile has also been largely destroyed, though its path can still be traced across the Giza plateau. The causeway was a covered walled corridor, probably decorated with painted reliefs that depicted scenes from the pharaoh's life, his military campaigns, his religious ceremonies, and the construction of the pyramid itself. The ancient historian Herodotus described the causeway as being decorated with carved figures and inscriptions, and he considered the causeway to be as impressive an achievement as the pyramid itself. The loss of the causeway's decorations is another significant gap in our knowledge. The reliefs that once covered its walls would have been an invaluable source of information about the Fourth Dynasty and about the construction process that produced the Great Pyramid. The comparison between the Great Pyramid and modern construction projects provides a useful perspective on the scale of the achievement and the sophistication of the organizational methods that made it possible. The Hoover Dam, one of the most famous construction projects of the 20th century, employed approximately 21,000 workers at its peak and took 5 years to complete, using the most advanced construction technology available in the 1930s, including electric power, internal combustion engines, pneumatic drills, and reinforced concrete. The Great Pyramid employed a comparable number of workers, approximately 20 to 30,000, and took approximately 20 years to complete, using copper tools, stone hammers, and human muscle. The comparison is not entirely fair. The Hoover Dam involved challenges of a different kind, including the diversion of a major river and the management of liquid concrete. But it illustrates the point that the organizational challenge of the Great Pyramid was comparable to the organizational challenges of major modern construction projects, and that the Egyptians met this challenge with an organizational sophistication that was, in its own way, as impressive as the technology of the 20th century. The Pyramid of Khufu was not the only structure built on the Giza plateau. The plateau contains two other major pyramids, the Pyramid of Khafre, Khufu's son, and the Pyramid of Menkaure, Khufu's grandson, as well as the Great Sphinx, several smaller Queen's pyramids, numerous mastaba tombs of court officials, and the workers' village and associated facilities. The entire complex was designed as a unified architectural ensemble, a sacred landscape that expressed, in stone and sand, the religious beliefs and the social hierarchy of the Old Kingdom Egyptian state. The construction of the Giza complex extended over several generations, from the reign of Khufu through the reign of Menkaure, and the continuity of the construction program demonstrates the stability of the Egyptian state and the durability of the institutional structures that managed the construction process. The experimental archaeology that has been conducted in recent decades to test various theories about the pyramid's construction methods has provided valuable data, though the experiments have also highlighted the difficulty of reproducing ancient techniques under modern conditions. The most famous of these experiments was conducted by the Japanese construction firm Obayashi in 1978, which attempted to build a small-scale replica of a pyramid using the methods that the Egyptians were believed to have used. The attempt was instructive. The team discovered that the methods were more difficult to execute than they had expected, that the coordination of the workforce required more sophisticated organization than they had anticipated, and that the process of quarrying, transporting, and placing the blocks was physically demanding to a degree that modern workers found surprising. The experiment did not disprove the feasibility of the Egyptian methods. but it demonstrated that the methods required a level of skill, coordination, and physical endurance that should not be underestimated. More recent experimental work has focused on specific aspects of the construction process: the quarrying of limestone using copper tools, the transport of blocks on wetted sand, the raising of blocks using various ramp configurations, and the cutting and finishing of casing stones. Each experiment has contributed to our understanding of the specific techniques that the builders may have used, and each experiment has reinforced the central conclusion that the construction was feasible using the tools and methods available to the Old Kingdom Egyptians, provided that the workforce was sufficiently large, sufficiently skilled, and sufficiently well organized. The Nova television experiment in 1997, in which the archaeologist Mark Lehner supervised a team of workers who attempted to quarry, transport, and place limestone blocks using ancient methods, provided particularly valuable data about the time and the labor required for each stage of the construction process. The experiment demonstrated that a team of 12 workers could quarry a block in approximately 2 days, that a team of 20 workers could transport the block across a distance of several hundred meters in approximately 1 day, and that the placement of the block required careful alignment and levering that took several hours. The data from the Nova experiment has been used by numerous scholars in their estimates of the workforce size and the construction timeline, and it provides one of the best available calibrations of the relationship between labor input and construction output for the specific methods that the Egyptians are believed to have used. The question of quality control during the construction process deserves particular attention because it addresses one of the most puzzling aspects of the pyramid's construction: the extraordinary consistency of the workmanship across the entire structure, from the precisely leveled base to the accurately angled casing, from the tightly jointed core blocks to the immaculately finished granite chambers. The consistency implies a system of quality control, a mechanism by which the work of individual teams and individual workers was checked against established standards and corrected when it fell short. The mechanism may have been as simple as regular inspections by skilled foremen who walked the construction site and checked the work in progress, or it may have involved more formalized procedures with measurements taken at regular intervals and recorded by scribes who tracked the accuracy of the construction course by course. The experimental archaeology conducted in recent decades has provided valuable data about the feasibility and the difficulty of the ancient construction methods. The most instructive experiments include the Japanese Obayashi Corporation's 1978 attempt to build a small replica pyramid, which revealed that the methods were more physically demanding and organizationally complex than the modern workers had anticipated, and the Nova television experiment of 1997, supervised by Mark Lehner, which demonstrated that a team of 12 could quarry a block in approximately 2 days, and a team of 20 could transport it several hundred meters in 1 day. These experiments have reinforced the central conclusion that the construction was feasible with ancient tools and methods, provided the workforce was sufficiently large, skilled, and well organized. The quality control systems that maintain the extraordinary consistency of workmanship across the entire structure deserve particular attention. The consistency, from the precisely leveled base to the accurately angled casing, from the tightly jointed core blocks to the immaculately finished granite chambers, implies formalized inspection procedures. Skilled foremen almost certainly walk the construction site regularly, checking work against established standards, while scribes recorded measurements and tracked accuracy course by course. The system ensured that the work of individual teams was held to uniform standards, producing the seamless geometric precision that characterizes the finished pyramid. The question of how the casing stones were placed and finished represents one of the most demanding aspects of the construction. The Tura limestone casing stones were cut with smooth exterior faces and angled interior faces that mated precisely with the underlying courses. The joints between adjacent stones were so tight that a knife blade cannot be inserted between them, implying specialized finishing techniques executed by master craftsmen. The final polishing was probably done from the top down as construction scaffolding was removed, transforming the rough-stepped structure into the smooth gleaming monument the builders intended. The capstone, the pyramidion that crowned the apex, was the final block placed, and almost certainly a moment of great ceremony. The capstone may have been granite covered in gold leaf or electrum, inscribed with religious texts dedicating the completed structure to the gods and to the pharaoh's eternal life. Its placement marked the culmination of 20 years of sustained national effort. The construction timeline has been analysed by numerous scholars who confirm that the 20-year period is tight but achievable. A workforce of 20 to 30,000, organised into efficient teams and supplied by a well-managed logistics system, could quarry, transport, and place the required blocks within the timeframe. The construction was almost certainly continuous year-round, with a permanent skilled workforce, supplemented by seasonal labourers during the flood, as evidenced by the scale of the permanent infrastructure at the workers' village and the logical impossibility of completing the project using seasonal labour alone. The question of workforce morale and motivation is one that modern management theorists find fascinating and that the ancient evidence addresses in suggestive, incomplete ways. The team names, inscribed on the blocks themselves and found in the graffiti of the stress-relieving chambers, suggest a system that encouraged group identity and competitive pride among the work teams. The generous rations, bread, beer, meat, and other provisions that exceeded what ordinary Egyptians consumed suggest a system that rewarded labour with material benefits that made the work attractive rather than merely compulsory. The medical care documented in the skeletal remains suggests a system that valued its workers' health and that invested in their recovery when they were injured. And the respectful burials in the workers' cemetery suggest a system that honoured its labourers in death as well as in life, treating them as valued members of a community rather than as expendable tools to be discarded when they were no longer useful. The combination of group identity, material reward, medical care, and respectful treatment creates a picture of a workforce that was motivated by something more complex than mere coercion, a workforce that participated in the construction with a degree of voluntary commitment that the slave labour myth does not account for. The workers may not have chosen to participate in building the pyramid in exactly the same way that a modern employee chooses a job, but they were not the brutalised, desperate slaves of popular imagination. They were participants in a national project, a great project that the entire culture considered profoundly important, that the state supported with generous resources, and that the workers themselves may well have regarded with a genuine and deeply felt mixture of obligation, pride, and genuine belief in the religious purpose that the project served. The scale of the support infrastructure at Giza, the bakeries, the breweries, the workshops, the storage facilities, the medical stations, the administrative offices, powerfully demonstrates that the Egyptian state understood a fundamental principle that modern organizations often forget. The overall effectiveness of a large workforce depends not merely on the size of the workforce alone, but on the quality of the support systems that sustain it. A well-fed, well-housed, properly equipped, and adequately rested worker produces more and better work than a hungry, homeless, poorly equipped one, and the investment in support infrastructure pays for itself many times over in the productivity gains it generates. The Egyptians understood this. The evidence from the workers' village proves it, and the Great Pyramid itself, the truly magnificent product of this comprehensively well-supported, efficiently organised, and genuinely motivated workforce, is the ultimate proof that the investment was worthwhile. The entire Giza complex, pyramids, temples, causeways, boat pits, and associated structures, represents one of the most ambitious and most coherent architectural programs in human history, a program that was sustained across 3 generations of pharaohs and that produced a sacred landscape of unparalleled monumentality. The Sphinx, the enormous lion body, human-headed statue that guards the eastern approach to the Giza complex, was carved from a single outcrop of limestone bedrock that was left standing when the surrounding stone was quarried for use in the pyramid's construction. The Sphinx is therefore a direct byproduct of the quarrying operation, a feature of the landscape that the builders chose to preserve and to transform into a monumental sculpture rather than to demolish for its stone. The decision to carve the Sphinx from the remaining bedrock was both pragmatic and symbolic. It made use of a feature that would otherwise have been an obstacle to the quarrying operation, and it created a monument that served as a guardian figure for the entire pyramid complex. The question of how the casing stones were placed and finished deserves detailed examination because it represents one of the most demanding aspects of the entire construction process and one of the least well understood. The casing stones were blocks of fine white limestone from the Tura quarries, a limestone that was harder, denser, and more uniform in colour than the local Giza limestone that constituted the bulk of the pyramid. The casing stones were cut to precise dimensions, with smooth faces on the exterior side and angled faces on the interior side that mated with the underlying courses of the pyramid. The exterior faces were polished to a smooth finish, creating the gleaming white surface that gave the pyramid its original spectacular appearance. The placement of the casing stones required a level of precision that exceeded what was needed for the core blocks. The joints between adjacent casing stones had to be tight, so tight that, as has been noted, a knife blade cannot be inserted between them. The exterior faces had to be aligned to create a smooth, continuous surface that maintained a consistent angle from base to apex. The finishing of the casing, the final polishing that produced the smooth exterior surface, was probably done from the top down, as the scaffolding or ramps that had been used during construction were progressively removed. The removal of the ramps and the finishing of the casing would have been the final phase of the construction process, the phase that transformed the rough, stepped structure of the core blocks into the smooth, gleaming pyramid that the builders intended. The capstone, the pyramidion, the small pyramid-shaped stone that crowned the apex of the structure, was the final block to be placed and was almost certainly a moment of great ceremony and celebration. The capstone may have been made of granite, covered in gold leaf or electrum, and inscribed with religious texts that dedicated the completed structure to the gods and to the eternal life of the pharaoh. The placement of the capstone marked the completion of the construction, the moment when 20 years of sustained effort reached its culmination and the greatest building project in the ancient world was finished. The construction timeline, 20 years for the entire project, from the preparation of the site to the placement of the capstone, has been analysed by numerous scholars and engineers who have attempted to determine whether the timeline is realistic, given the number of blocks, the size of the workforce, and the methods that were available. The consensus is that the timeline is tight but achievable, that a workforce of 20 to 30,000 workers, organised into efficient teams and supplied by a well-managed logistics system, could have quarried, transported, and placed the required number of blocks within the 20-year time frame. The analysis depends on assumptions about the efficiency of the quarrying process, the speed of the transport system, the rate of block placement, and the proportion of the workforce dedicated to each phase of the construction. Assumptions that are difficult to verify given the limited evidence, but that are consistent with the archaeological data that is available. The question of whether the construction was continuous or seasonal is another aspect of the timeline debate. Some scholars have argued that the construction was limited to the flood season, the period of approximately 3 months each year when the agricultural fields were underwater and the rural population was available for state labour. Others have argued that the construction was continuous throughout the year, with a core workforce of skilled professionals working year-round and supplemented by seasonal labourers during the flood. The evidence supports the continuous construction hypothesis, the scale of the permanent infrastructure at the workers' village, the year-round nature of the food supply facilities, and the logical impossibility of completing the pyramid within a 20-year time frame using only seasonal labour, all suggest that the construction was an ongoing, full-time operation that employed a permanent workforce supplemented by seasonal rotations. The sixth exploration examines the legacy of the Great Pyramid, what it tells us about the civilization that built it, and what its survival across 45 centuries means for our understanding of human achievement. The Great Pyramid is not merely a tomb, it is an argument made in stone about what human beings are capable of when they organize themselves, commit their resources, and sustain their effort over decades. The pyramid argues that the limits of human achievement are not determined by the tools we possess, but by the knowledge we accumulate, the organizations we build, and the will we bring to the task. The builders of the Great Pyramid did not have steel, they did not have engines, they did not have computers. They had copper and stone and wood and water and rope, and they built the largest, most precise stone structure in the history of the world. The tools were simple, the achievement was not. Step back now from the details of quarrying and ramps and internal chambers and workforce logistics. Step back from the specific engineering problems and the specific solutions that the builders employed. Step back from the Great Pyramid as an engineering project and look at it as something else, as a statement about what it means to be human, about what human beings can accomplish when they commit themselves to a goal that exceeds the lifetime of any individual, and that requires the sustained cooperation of tens of thousands of people across 2 decades of concentrated effort. The Great Pyramid is the oldest surviving structure on Earth that was built to a scale that exceeds anything nature produces in a comparable climate. It has survived 4,500 years of earthquakes, sandstorms, floods, and the deliberate depredation of human beings who stripped its casing, tunneled into its interior, and used its stones for their own purposes. It has survived the rise and fall of every empire that has existed since its construction. The Assyrian, the Persian, the Greek, the Roman, the Arab, the Ottoman, the British, and the modern Egyptian state. It has survived because it was built to survive, because the engineers who designed it understood the forces that would act on the structure over time, and because they built it with a margin of safety that has proven sufficient to withstand everything that 45 centuries of history have thrown at it. Let that sink in. A structure built 4,500 years ago, built with copper tools and human muscle, has outlasted every other structure on Earth, not because it was protected, not because it was maintained, but because it was built right. The engineering was sound, the materials were appropriate, the design was correct, and the execution. The placement of 2,300,000 blocks of stone, with a precision that modern engineers still study with respect, was as close to flawless as any construction project in human history. The pyramid forces a reckoning with our assumptions about the past, our assumptions about the capabilities of ancient peoples, about the relationship between technology and achievement, and about the nature of progress itself. We tend to assume that progress is linear, that the past was primitive and the present is advanced, that ancient peoples were limited by their tools and that modern peoples are empowered by theirs. The Great Pyramid challenges this assumption. It demonstrates that a civilization with simple tools can achieve results that a civilization with complex tools cannot easily replicate, not because the ancient civilization possessed secret knowledge or supernatural assistance, but because it possessed something that is, in many ways, more valuable than technology: institutional knowledge accumulated over generations about how to work with specific materials in specific conditions to achieve specific results. This institutional knowledge, the knowledge of how limestone behaves under compression, how granite responds to pounding, how water levels surfaces, how ramps distribute loads, how teams of workers can be organized to maximize efficiency, was the real technology of the pyramid builders. It was not written in textbooks, it was not stored in databases. It was held in the minds and the hands and the muscles of the thousands of workers who participated in the construction. Passed down from master to apprentice, from foreman to laborer, from one generation of builders to the next. The knowledge was practical rather than theoretical. It was knowledge of what works rather than knowledge of why it works, knowledge gained through experience rather than through experimentation in the modern scientific sense. The modern study of the Great Pyramid has been transformed in recent decades by the application of new technologies. Technologies that allow researchers to examine the interior of the pyramid without physically entering it and to detect features that are invisible to the naked eye. The most significant of these technologies is muon tomography, a technique that uses naturally occurring subatomic particles called muons to create images of the internal structure of large objects in much the same way that medical X-rays create images of the internal structure of the human body. In 2017, the Scan Pyramids Project, an international collaboration involving researchers from Egypt, France, and Japan, announced the discovery of a large void within the body of the Great Pyramid, located above the Grand Gallery and extending for approximately 30 meters. The void was detected using muon tomography. The researchers placed muon detectors inside and around the pyramid and measured the rate at which muons pass through different parts of the structure. The rate of muon passage is determined by the density of the material the muons pass through. Stone blocks more muons than empty space, and the measurements revealed a region above the Grand Gallery where the muon rate was significantly higher than expected, indicating the presence of a large cavity within the pyramid's mass. The discovery of the void was one of the most significant archaeological findings of the 21st century, the first major new discovery about the internal structure of the Great Pyramid in more than 2 centuries. The nature and the purpose of the void remain unknown. It may be a structural feature designed to reduce the weight above the Grand Gallery. It may be a construction gap left by the builders for reasons related to the construction process, or it may be a previously unknown chamber that served a specific ritual or functional purpose. The resolution of this question will require further investigation, possibly involving additional muon tomography scans, possibly involving the deployment of miniaturized robots that could enter the void through small drilled openings, or possibly involving other non-invasive technologies that have not yet been developed. The Scan Pyramids discovery is a reminder that the Great Pyramid has not yet revealed all its secrets, that 4,500 years of exploration and study have not exhausted the structure's capacity to surprise. The pyramid is, in a sense, still being discovered, still yielding new information, still challenging our understanding of its construction and its purpose, still demonstrating that the builders of the Old Kingdom created a structure whose complexity exceeds what generations of subsequent scholars have been able to fully comprehend. And it gets stranger, because the knowledge that built the Great Pyramid was, to a significant extent, lost. Not immediately. The Egyptians continued to build pyramids for centuries after Khufu's reign, and the techniques of pyramid construction were transmitted from one generation of builders to the next. But the scale declined, the precision declined, the ambition declined. No pyramid built after the 4th dynasty matched the Great Pyramid in size, in precision, or in the sophistication of its internal structure. The knowledge that had made the Great Pyramid possible was, over the centuries, gradually eroded. As the political and economic conditions that had supported the construction program changed, as the institutional structures that had maintained the knowledge were reformed or dismantled, and as the practical expertise of the master builders was diluted by the passage of time and the accumulation of changes in technique and approach. Let that sink in. The civilization that built the Great Pyramid could not, a few centuries later, replicate its own achievement. The knowledge was not lost in a single catastrophic event. It was not destroyed by an invasion or a natural disaster. It was lost gradually, eroded by the same processes of institutional change and generational turnover that erode every form of institutional knowledge in every civilization. The loss is a warning, a demonstration of how fragile even the most impressive achievements can be when the institutional structures that produce them are not maintained. The Great Pyramid is often described as a tomb, and it was, in the most literal sense, designed to house the body of the pharaoh Khufu for eternity. But the pyramid was far more than a tomb. It was a machine for eternity, a structure designed not merely to protect the pharaoh's body, but to facilitate his transformation from a mortal king into an immortal god, to maintain the connection between the living and the dead. and to ensure the continuation of the cosmic order that depended on the pharaoh's eternal survival among the gods. The religious function of the pyramid shaped every aspect of its design, from the orientation of the base to the cardinal points, connecting the structure to the cosmic axes that the Egyptian religious system considered fundamental to the order of the universe, to the internal chambers that housed the pharaoh's body and his funerary equipment, to the ventilation shafts that may have served as conduits for the pharaoh's soul to travel to the stars. The pyramid was not merely a building, it was a cosmic instrument, a structure that was designed to interact with the fundamental forces of the universe in ways that the Egyptian religious system considered essential for the pharaoh's eternal survival. The concept of the afterlife that the pyramid was designed to serve was not the simple, passive heaven that modern religious traditions often imagine. The Egyptian afterlife was active, demanding, and fraught with danger, a realm in which the deceased pharaoh had to navigate a complex series of trials and transformations, assisted by the spells and the rituals that were inscribed on the walls of later pyramids, and that were almost certainly performed at the time of Khufu's burial as well. The pyramid was the staging ground for this eternal journey, the place where the pharaoh's body was prepared, where the rituals were performed, and where the transformation from mortal to immortal began. The funerary complex that surrounded the pyramid, the mortuary temple on the eastern face, the causeway that connected the mortuary temple to the valley temple near the Nile, the boat pits that contained the dismantled boats that would carry the pharaoh through the celestial waters of the afterlife, was an integral part of the pyramid's function. The complex was designed as a complete system, a system in which each element served a specific ritual purpose, and in which the pyramid itself was the central and most important component. The mortuary temple was the place where the daily rituals of offering and prayer were performed, rituals that were intended to sustain the pharaoh's soul in the afterlife, and that were maintained by a dedicated priesthood for generations after the pharaoh's death. The loss of the knowledge that built the Great Pyramid is itself one of the most profound lessons of the pyramid's story, a lesson about the fragility of institutional knowledge and the vulnerability of even the most impressive civilizations to the slow but relentless erosion of their own hard-won capabilities. The decline of pyramid building after the Fourth Dynasty was not sudden. It was gradual, a slow diminishment that extended over several centuries and that reflected changes in the political, economic, and religious landscape of the Egyptian state. The Fifth Dynasty pharaohs built pyramids, but they were smaller, less precise, and less ambitious than the pyramids of the Fourth Dynasty. The Sixth Dynasty pharaohs built smaller pyramids still. By the Middle Kingdom, roughly 500 years after the Great Pyramid, the Egyptians were building pyramids of mud brick rather than stone, structures that have largely disintegrated over the millennia. The knowledge that had made the Great Pyramid possible was not lost in a single catastrophic event. It was attenuated, diluted by the passage of time, eroded by changes in political priorities, and gradually forgotten as the institutional structures that had maintained it were reorganized or disbanded. The process by which the knowledge was lost mirrors processes that are familiar in the modern world. The loss of manufacturing knowledge when factories close, the loss of craft skills when apprenticeship systems are abandoned, the loss of institutional memory when organizations are restructured and experienced personnel are replaced by newcomers who lack the accumulated knowledge of their predecessors. The loss is rarely dramatic. It is usually gradual, so gradual that the people experiencing it may not realize what is happening until the knowledge is gone and the capability it supported has been irretrievably lost. The implications for the modern world are sobering. Our own civilization possesses capabilities that are, in many respects, far more impressive than the capabilities of the Old Kingdom Egyptians. We can build structures that are taller, more complex, and more technologically sophisticated than the Great Pyramid. But our capabilities are also more fragile. They depend on supply chains that span the globe, on digital infrastructure that is vulnerable to disruption, on specialized knowledge that is held by a small number of people, and on institutional structures that are constantly being reorganized in ways that can destroy accumulated knowledge without replacing it. The Great Pyramid has survived for 4,500 years. How many of our own most impressive structures would survive for a fraction of that time if the institutional knowledge that maintains them were lost? The question is not hypothetical. The modern world has already experienced episodes of knowledge loss that parallel, in miniature, the loss of pyramid-building knowledge in ancient Egypt. The technology of the Saturn V rocket, the vehicle that carried the Apollo astronauts to the moon, has been largely lost, not because the documentation was destroyed, but because the institutional knowledge that was needed to interpret the documentation and to translate it into a functioning rocket was held in the minds of the engineers who designed and built the vehicle, and those engineers have retired or died. The knowledge was not in the blueprints, it was in the people, and when the people were gone, the knowledge went with them. The fragility of institutional knowledge is not merely a historical observation, it is a contemporary reality, a reality that the modern world is experiencing in real time as the institutional structures that maintain our most critical capabilities are subjected to the same pressures of reorganization, budget reduction, and generational turnover that eroded the pyramid-building knowledge of the Old Kingdom Egyptians. The knowledge that maintains our nuclear power plants, our electrical grids, our water treatment systems, and our digital infrastructure is held. Like the knowledge that built the Great Pyramid, primarily in the minds of the people who operate and maintain these systems. If these people are lost through retirement, through budget cuts, through organizational restructuring, through the simple failure to train replacements, the knowledge goes with them, and the systems that depend on the knowledge become vulnerable to failure. The question of what the modern world can learn from the Great Pyramid is a question that transcends the specifics of ancient engineering and touches on the deepest challenges facing contemporary civilization. The pyramid teaches that sustained effort maintained across decades rather than months, across generations rather than individual careers, can produce results that are literally monumental. The modern world is not well suited to sustained effort. Our political cycles are measured in years. Our corporate planning horizons are measured in quarters. Our attention spans are measured in news cycles. The kind of 20-year commitment that produced the Great Pyramid, a commitment that required the sustained focus of an entire civilization on a single goal, maintained through changes in personnel, through crises and setbacks, through the inevitable and entirely natural fluctuations of enthusiasm and energy that accompany any long-term project, is alien to the modern sensibility. We admire the result. We struggle to replicate the process. The pyramid also teaches that the relationship between a civilization and its greatest achievements is more fragile than it appears. The civilization that built the Great Pyramid could not, a few centuries later, build anything comparable. The knowledge was lost, not through catastrophe, but through the gradual, imperceptible erosion of institutional capability that accompanies every change in organizational structure, every consequential shift in political priorities, and every inevitable transition from one generation of experienced practitioners to the next. The lesson is directly relevant to the modern world, where the vital institutional knowledge that maintains our most critical and most essential systems is under relentless and constant pressure from budget cuts, organizational restructuring, and the retirement and departure of experienced personnel who are not being replaced or trained at a sufficient rate to maintain continuity. The modern world's relationship with the Great Pyramid is characterized by a paradox. We admire the result while struggling to understand the process. We celebrate the achievement while failing to appreciate the institutional foundations that made it possible. The paradox reflects a broader cultural tendency to focus on products rather than processes, on outcomes rather than the organizational systems that produce them, on the visible monument rather than the invisible infrastructure of knowledge, logistics, and human coordination that was required to create it. The Great Pyramid is often treated as a mystery, a puzzle to be solved, a question to be answered. But the real significance of the pyramid lies not in the mystery, but in the answer. Not in what we do not know, but in what we do know, which is that a civilization working with simple tools and extraordinary knowledge built the largest, most precise, and most enduring stone structure in human history. The answer is not mysterious, it is humbling. It tells us that the limits of human achievement are not determined by our tools, but by our knowledge, our organization, and our will. It tells us that the ancient world was decidedly and demonstrably not primitive, that the human beings who lived and worked 4,500 years ago were every bit as intelligent, as capable, and as creative, and as determined as the people who live in the world today. And it tells us that the greatest and most enduring achievements of human civilization are not the products of individual genius, but of collective effort, the sustained, carefully coordinated, and methodically organized labor of thousands of ordinary people working together toward an extraordinary goal. The erosion of institutional knowledge is one of the most underappreciated risks facing complex civilizations, a risk that operates silently, gradually, and often invisibly until the moment when the knowledge is needed and discovered to be gone. The Great Pyramid stands as a reminder, a physical, visible, undeniable reminder, that human achievements, however impressive, are only as durable as the knowledge that created them. The pyramid itself has survived because it was built of stone, a material that is inherently durable and that does not require maintenance or updating to continue performing its structural function. But the knowledge that built the pyramid has not survived. It was lost, gradually and irreversibly, as the institutional structures that maintained it were changed, and the people who held it were replaced by people who held different knowledge. The stone endures, the knowledge does not, and the gap between the enduring stone and the lost knowledge is the most important lesson that the Great Pyramid teaches. The lesson that building something great is not enough, that the knowledge that makes greatness possible must be actively maintained, actively transmitted, and actively protected against the erosion that time and institutional change inevitably produce. The parallel with the Great Pyramid is direct and unsettling. The knowledge that built the pyramid was not in the tools, it was in the people, in the quarrymen who knew how limestone fractures, in the masons who knew how to shape a block to within millimeters of its intended dimensions, in the surveyors who knew how to align a base to true north, using nothing more than the stars and a plumb line, in the foremen who knew how to organize a team of 20 men to move a block weighing 2.5 tons across 100 meters of sand. The knowledge was intensely practical, deeply experiential, and physically embodied, stored in human minds and human hands rather than in documents or databases. And when the institutional structures that maintained the knowledge were changed, when the pharaohs stopped building pyramids on the scale of the Fourth Dynasty, when the workforce was redirected to other projects, when the master builders retired and their apprentices were assigned to different tasks, the knowledge faded and the capability it supported was lost. The parallel with our own civilization is uncomfortable but important. The modern world possesses technological capabilities that far exceed anything available to the ancient Egyptians. But the modern world also possesses vulnerabilities that the ancient Egyptians did not face. Vulnerability related to the complexity and the interconnectedness of our technological systems, the fragility of the digital infrastructure on which our knowledge is stored, and the specialization of our workforce, which means that the knowledge needed to maintain our most critical systems is concentrated in the hands of a very small number of people. The Great Pyramid has survived for 4,500 years. How many of our most important structures, our most critical systems, our most essential technologies would survive for even a fraction of that time if the institutional knowledge that maintains them were lost? The Great Pyramid stands on the Giza Plateau in the early morning light, its shadow stretching westward across the desert toward the vast emptiness of the Sahara. It has stood there for 4,500 years. Through the entire recorded history of human civilization, through the rise and fall of every empire that has existed since its construction, through wars and plagues and famines and revolutions, and the slow, patient erosion of time, it has watched as the civilization that built it declined and was conquered. by the Persians, by the Greeks, by the Romans, by the Arabs, by the Ottomans, by the British. It has watched as the language of its builders was forgotten and then rediscovered, as the hieroglyphic script was deciphered and the ancient texts were read for the first time in 2,000 years. It has watched as the modern world grew up around it, the sprawling metropolis of Cairo pressing against its western edge, the traffic and the noise and the pollution of a city of 20 million people lapping at the base of a structure that was old when Rome was young. The pyramid is patient. It does not care about the traffic. It does not care about the tourists. It does not care about the theories that have been proposed to explain its construction, or the debates that have raged among scholars about the details of its engineering. The pyramid simply exists, a fact of stone, a monument of mass, a structure that communicates through its sheer physical presence, a message that transcends language and culture and time. We were here. We were capable of this. We built something that would outlast us, not by centuries but by millennia. The message is humbling. It is also instructive. The Great Pyramid teaches us that the relationship between technology and achievement is not what we assume it to be. That simple tools in the hands of knowledgeable, organized, motivated people can produce results that complex tools cannot replicate. The pyramid teaches us that institutional knowledge, the accumulated practical wisdom of generations of skilled workers, is the most valuable and the most fragile form of technology that any civilization possesses. The pyramid teaches us that the difference between a civilization that can build something extraordinary and a civilization that cannot is not a difference of tools or materials or resources. It is a difference of organization, of the ability to coordinate the efforts of thousands of people toward a single goal over a sustained period of time. The Great Pyramid's survival into the modern era, its endurance through the centuries of medieval stone robbing, through Napoleon's Egyptian campaign, through the British colonial period, and through the explosive growth of modern Cairo, is itself a story of resilience that deserves to be told. The pyramid has not survived passively. It has survived despite sustained assault. The systematic removal of its casing stones during the medieval period stripped the pyramid of its exterior finish and reduced its height by several meters, exposing the rough core blocks that were never intended to be seen. The tunneling of the Caliph al-Ma'mun in the 9th century of the Common Era created a forced entrance through the pyramid's north face, an entrance that bypassed the original concealed entrance and that has been used by every subsequent visitor, from medieval treasure hunters to modern tourists. The pyramid has been climbed, excavated, surveyed, photographed, scanned, and subjected to every form of investigation that human curiosity and technological capability have made possible. And yet the pyramid endures. It has lost its casing, it has lost its capstone, it has lost the treasures that were buried within it. It has lost the mortuary temple and the valley temple and the causeway that were integral parts of its original complex. But it has not lost its essential structure. The 2,300,000 blocks of limestone and granite that constitute its mass are still in place, still bearing the loads that the builders designed them to bear, still demonstrating the precision and the durability that 4,500 years of survival have confirmed. The pyramid is diminished but not destroyed. It is scarred but not broken. It stands, patient, massive, silent, waiting for the next 4,500 years with the same indifference to time that it has displayed throughout the first. The question of what the Great Pyramid means, what it tells us about the civilization that built it, and what lessons it holds for the civilizations that have followed, is a question that has been asked by every generation that has stood in its shadow. The answers have varied, from Herodotus, who saw it as evidence of a tyrant's vanity and the suffering of the enslaved workers who built it, to Napoleon, who saw it as evidence of a civilization's grandeur and calculated that its stones could build a wall around France, to the modern archaeologists, who see it as evidence of a sophisticated, well-organized state that was capable of mobilizing and coordinating human effort on a scale that the ancient world had never seen before and would rarely see again. The modern archaeological understanding of the pyramid is, in many ways, the most respectful of these interpretations. because it gives credit where credit is due to the people who actually built the structure. The workers were not slaves. They were not aliens. They were not the dupes of a tyrant. They were skilled professionals, masons, quarrymen, surveyors, boatmen, scribes, and labourers who participated in a national project that they believed was important and that they executed with a level of competence and a commitment to quality that is evident in every block, every joint, every alignment of the finished structure. The pyramid is also a statement about the relationship between a civilization and its dead, about the belief which the Egyptians held with a conviction that permeated every aspect of their culture, that the dead were not gone but merely transformed, that the afterlife was not a metaphor but a reality, and that the living had an obligation to provide for the dead in ways that were both material and spiritual. The pyramid was built to serve the dead pharaoh in the afterlife, to house his body, to protect his possessions, to facilitate his transformation from a mortal king into an eternal god. The scale of the pyramid reflects the scale of the obligation, the belief that the pharaoh's eternal well-being required the mobilization of an entire civilization's resources, and that the investment was worthwhile because the pharaoh's survival in the afterlife was essential to the continued prosperity and stability of the living. This belief may seem strange to modern observers, irrational, extravagant, perhaps even absurd. But the belief produced the pyramid, and the pyramid has survived for 4,500 years. The beliefs that modern civilizations invest their resources in economic growth, military power, technological innovation may seem more rational, more practical, more defensible. But will the products of these beliefs survive for 4,500 years? Will our skyscrapers, our bridges, our dams, our server farms endure as long as the Great Pyramid has endured? The question is not rhetorical, it is genuinely uncertain, and the uncertainty should give us pause, because it suggests that the Egyptians understood something about permanence, about the relationship between effort and durability, about the kind of construction that lasts, that our own civilization, for all its technological sophistication, may not fully appreciate. The question of what we have lost, what knowledge about the pyramid's construction has been destroyed by time, by the condemnation of the Old Kingdom's institutional records, by the fragility of papyrus, and by the simple passage of 4,500 years, is a question that the Diary of Merer makes painfully concrete. The diary is a single document, a fragment of a vast bureaucratic apparatus that must have generated thousands of similar records over the 20 years of the pyramid's construction. Most of those records have been lost. The administrative papyri that documented the quarrying, the transport, the placement, the alignment, the supervision, and the supply of the construction project are gone, destroyed by humidity, by insects, by fire, by the simple decomposition of organic material over millennia. The loss is incalculable. The diary tells us what one crew of 200 workers did during a few months of the construction. The thousands of records that have been lost would have told us what every crew did during every month of the entire 20-year project, providing a complete, detailed, day-by-day account of the most ambitious construction project in the ancient world. The loss of these records is not merely an academic inconvenience. It is the reason that the debate about the pyramid's construction methods continues. The reason that scholars still argue about ramps and levers and counterweights, the reason that engineers still propose new theories and architects still build new models. The reason that the question of how the pyramid was built remains, after more than a century of modern archaeological investigation, a question that has not been definitively answered. The answers were in the records. The records are gone, and the gap between what we know and what we need to know to fully understand the pyramid's construction is the measure of the loss, the measure of what time and fragility have taken from us. The relationship between the Great Pyramid and the modern city of Cairo, which has grown to within a few hundred meters of the Giza plateau, encapsulates the tension between preservation and development that characterizes the modern world's relationship with its ancient heritage. The pyramid was built in the desert, on a plateau that was deliberately chosen for its remoteness from the inhabited lowlands. The desert that once separated the pyramid from the nearest settlement has been consumed by the expanding metropolis, replaced by apartment buildings, roads, fast food restaurants, and the infrastructure of a modern city of more than 20 million people. The pyramid now stands at the edge of the city rather than at the edge of the desert, a juxtaposition that is jarring, surreal, and somehow appropriate, because it places the most enduring product of the ancient world directly alongside the most ephemeral products of the modern world, and invites the viewer to consider which will last longer: the preservation of the Giza Plateau, the protection of the pyramid and its associated structures from the encroachment of development, from the damage caused by pollution and vibration, and from the wear inflicted by millions of tourists who visit the site each year, is one of the most important and one of the most challenging preservation tasks in the world. The Egyptian government, in collaboration with international organizations and archaeological institutions, has undertaken numerous initiatives to protect the site, including restrictions on construction near the plateau, programs to reduce pollution in the surrounding area, and conservation projects designed to stabilize and preserve the remaining casing stones and the internal chambers. The work is ongoing, and it will need to continue for as long as human civilization values its connection to its own past. The answer to the question posed by the title of this documentary, "How was the Great Pyramid actually built?" is therefore not a single answer but a composite one. It was built with limestone and granite. It was built with copper tools and stone hammers. It was built with wooden sledges and water and rope. It was built with ramps, probably a combination of external ramps for the lower courses and some form of internal or adapted ramp for the upper courses. It was built with astronomical observations for alignment and water channels for leveling. It was built with a labor force of 20 to 30,000 workers, skilled craftsmen and temporary laborers, organized into teams, fed by the state, and motivated by a combination of religious devotion, national pride, and the practical incentives of good wages and generous rations. But above all, it was built with knowledge, the accumulated, practical, hard-won knowledge of a civilization that had been building in stone for more than a century, a civilization that had learned from its failures, refined its techniques, perfected its methods, and produced, at the moment of its greatest ambition, a structure that would stand as a monument to human capability for the rest of recorded time. The knowledge was the real technology. The stones were just the material. The Great Pyramid of Giza was built by human beings. This is the answer. It is the only answer that the evidence supports, and it is the only answer that does justice to the people who built it. The quarrymen who cut the stone, the masons who shaped it, the laborers who dragged it across the desert and up the ramps, the surveyors who aligned the base and the sides, the engineers who designed the internal chambers and the stress-relieving structures, the scribes who recorded the deliveries and the work schedules, the foremen who organized the teams and supervised the work, the bakers who baked the bread, and the brewers who brewed the beer, and the physicians who set the broken bones. The pyramid was built by people, named people. People like Mera, the inspector whose diary records the mundane details of limestone transport with the precision of a shipping clerk. Anonymous people. The thousands of workers whose names are lost but whose labor is preserved in every block of every course of the pyramid they built. The claim that the pyramid was built by aliens, by lost civilizations, by anyone other than the Egyptians of the Old Kingdom is not merely wrong, it is an insult to the intelligence, the skill, the dedication, and the organizational genius of the people who actually did the work. It is an insult that robs one of the greatest civilizations in human history of its most impressive achievement, and it is an insult that is rooted, whether its proponents acknowledge it or not, in the assumption that an ancient African civilization could not have been capable of building something so magnificent. The assumption is false. The evidence is clear. The Egyptians built the pyramid. They built it with knowledge, with labor, with organization, and with a commitment to permanence that has been vindicated by 4,500 years of survival. The pyramid still stands. The casing stones are gone, stripped by medieval builders who needed the limestone for mosques and palaces. The capstone is gone, lost to time or to the same scavengers who took the casing. The interior has been explored, looted, and studied by generations of archaeologists, treasure hunters, and tourists. The pharaoh for whom it was built, Khufu, the ruler of the 4th dynasty, the king whose name appears in the stress-relieving chambers above the king's chamber in the red ochre marks of the workers who placed the stones, has been dead for 4.5 millennia. His mummy has not been found. His treasures are gone. His name is remembered only because of the structure he commissioned. But the structure endures. 2,300,000 blocks of limestone and granite, placed with a precision that modern engineers still study, standing on a base that is level to within 2 centimeters across 13 acres of bedrock, aligned to true north with an accuracy that would satisfy a modern surveyor, surviving earthquakes and sandstorms, and the deliberate destruction of its outer surface. The pyramid endures. It is the oldest large-scale structure on Earth. It is the last surviving wonder of the ancient world. It is the physical proof that human beings, working with simple tools and extraordinary knowledge, are capable of building something that time itself cannot destroy. The pyramid was built to last forever. The builders designed it with that intention, choosing materials for their durability, designing the structure for its stability, and executing the construction with a precision that was driven not by vanity, but by the conviction that the pharaoh's eternal resting place must be as permanent as the earth itself. The design was correct, the materials were appropriate, the execution was meticulous, and the pyramid has, so far, fulfilled its builder's intention, surviving intact through 4,500 years of earthquakes, sandstorms, floods, invasions, and the deliberate efforts of human beings to dismantle and repurpose its components. The survival of the pyramid is not merely a matter of engineering. It is a matter of design philosophy, a philosophy that prioritized permanence over convenience, durability over economy, and long-term survival over short-term efficiency. The builders chose limestone because it is durable. They chose a pyramidal shape because it is inherently stable. The wide base distributes the weight, the sloping sides deflect lateral forces, and the geometric simplicity of the form minimizes the structural vulnerabilities that could lead to failure. They chose to build on bedrock because bedrock does not settle or shift. Every decision, from the choice of site to the choice of materials to the choice of form, was made with permanence in mind. And the cumulative effect of these decisions is a structure that has survived longer than any other large-scale human construction on Earth. The workers who built the pyramid did not know that they were building the last surviving wonder of the ancient world. They did not know that the structure they were creating would outlast the Hanging Gardens of Babylon, the Colossus of Rhodes, the Lighthouse of Alexandria, and every other monument on the list of wonders that the ancient Greeks would compile more than 2,000 years later. They did not know that the structure would survive the fall of every empire that would succeed their own: the Assyrian, the Persian, the Macedonian, the Roman, the Byzantine, the Arab, the Ottoman, and the British. They knew only that they were building the pharaoh's tomb, the eternal resting place of their divine king, the structure that would ensure his survival among the gods, and that would, by ensuring his survival, ensure the continued prosperity and stability of the land they called the Two Lands. They built well. They built with the accumulated knowledge of a century of pyramid construction. They built with limestone and granite and copper and wood and water and rope. They built with organization and dedication and the quiet, daily, unremarkable labor of people who went to work each morning and did their jobs, and went home each evening and did the same thing again the next day for 20 years until the job was done. The job was done 4,500 years ago. The pyramid still stands. The workers are gone, their bones in the cemetery, their names on the blocks, their bread in the ashes of the bakeries, their beer in the residue of the breweries. They are gone, but what they built remains. Massive, silent, patient, enduring, the most eloquent argument in stone that human beings have ever made for the proposition that ordinary people, working together, can create something extraordinary. The question was, how was it actually built? The answer is, with everything a civilization had, with its stone and its copper and its wood and its water, with its labor and its organization and its administrative genius, with its religious conviction that the pharaoh's tomb was the most important structure in the kingdom, with its institutional knowledge, the hard-won accumulated wisdom of generations of skilled builders who learned systematically from failure and refined their methods through a century of experimentation, with its people, the 20,000 men and women who lived and worked at the Giza Plateau, who ate their bread and drank their beer and set their broken bones and went back to work the next morning, moving one more block, placing one more stone, building one more course of the structure that would outlast everything they knew. The morning light catches the pyramid and turns it golden. The same light that the builders saw, the same light that Khufu saw, the same light that has risen over the Giza Plateau every day for 4,500 years. The light does not change. The pyramid does not change. The sand shifts. The city grows. The tourists come and go. But the pyramid stands, as it has always stood, as it was built to stand. A monument to the knowledge, the labour, and the extraordinary organisational genius of a civilization that understood, better than most, that the measure of a people is not what they consume but what they create, not what they destroy but what they build, and not what they forget, but what they leave behind for the generations that follow. They built something that would last forever, and it has, so far, 4,500 years and counting. The pyramid stands. The workers who built it are dust, but their achievement remains. The most eloquent statement in stone that human civilization has ever made, a statement that says, we were here, we were capable, and what we built will stand when everything else has fallen. The desert wind blows across the Giza Plateau. The sand gathers at the base of the pyramid. The sun rises and sets, as it has for 4,500 years, over a structure that was built to honour the dead, and that has become, across the millennia, a monument to the living, to the knowledge, the labour, and the extraordinary ambition of the human beings who looked at a limestone plateau in the desert and saw, in their minds, the shape of eternity.